What's up, guys? Tim Halston with DragBoss Garage University, and welcome Darin Morgan from DMI, Darin Morgan Induction. So tonight's live chat was a little bit of a misnomer, we'll say. And I want to welcome some of the guys here because one of them asked a question that's going to kind of bring us right into what we're going to say. We appreciate the members that are here and also anybody that's on YouTube because this is an open chat. There's no cost for it. So we'll see what we have. We already have 12 people here. So Brian Ellings, he's a new member with DBGU and DMI. Thanks, Brian, for joining. Ty Hewitt, damn Mopar people, they're still here. So good evening, guys. Don Daughter, he's a Chevy man. He's here. That's good to see you. Mariano Liano, he's from Argentina. He's a six-cylinder man. He loves six-cylinders, so we're going to do some work with those somewhere along the line. And we got plenty of time to get things done. But the Nova man, so he must like Novas. He says, Tim, is the broken pickup in the picture the cause of your loss of oil pressure? Now, when I made the little thumbnail for this, that's exactly what that was. And if you look at that picture, it's got a windage tray in it from Ford Performance Solutions. Actually, my buddy sent that to me, and I used that. When I made this, I said windage tray, a waste of time with like a question mark, so to speak. Now, this talk, this presentation, this chat is really friction power, windage control. It's not just about windage trays, but I kind of got that to kind of get people in and hook them because I had many people say, oh no, windage trays work. They make horsepower. You got to run a windage tray, blah, blah, blah. So I think when people saw that, the way I titled it, that's what they think we're just going to talk about. So there's a lot of things that determine if you're going to make horsepower, especially when it comes down to friction control and windage control. That windage tray you saw, did it make horsepower? I have no idea. I put the motor back together. Without it, it's running pretty close to the same. I don't know. And that's what Darin's going to come here and discuss with you, because it's not just doing an experiment and putting it on a dyno. Yep, it made 10 more horsepower. It's about 40 years of experience with pretty much every engine out there in design to help formulate a thesis, a theory, or an opinion. So Eric McMahon, good to see you here. Jeff Ott, good to see you here. So we're going to try not to be getting into a lot of questions right now. Let Darin present this, and let's see what we can learn. We got 28 people here, so let's roll, Darin.
Well, when you were talking about windage trays, basically, I mean, everybody wants to swing one way or the other, right? To extremes, of course. All windage trays are junk, and you have to have a windage tray. Well, somewhere in between there is the actual truth. And the truth is, in a wet sump, a lot of times you need a properly designed windage tray. Okay. The key point there is properly designed. You can hurt power just as easily as you can make it, and you can hurt it just as easily as you can help it. I have, excuse my cough, and I have a bit of cold. I have a lot of pictures of different ways to control the windage, but what are we talking about with windage? We're trying to control the oil, get it off the crank, into the oil pan so the sump can return it to the engine. Basically, that's what we're trying to do. And when you have a wet sump and a narrow pan, the crank just wants to hold the oil. And you have to have something to, for the lack of a better term, rip it off or suck it off. And a sump, a dry sump, in certain instances, which I'll show you, will literally rip the oil from the crank. But if you stick a scraper in there, scrapers are almost never a good answer. They're a Band-Aid. They're a Band-Aid for the fact the crank wants to hold the oil and pick it back up, and you have to rip it off the crank. Well, there's a frictional power loss for doing that. It costs you power to scrape that oil off the crank, and the amount, and it would shock you to find out actually how much it is. But every instance, intended use dictates design. Sometimes frame rails are narrow. You've got headers stuffed under there. You have to have a narrow pan. You're stuck. So you have to have a scraper and cost yourself that power in order to return the oil to the sump. Okay, so it's not all about making power. It's a balance of controlling the oil flow back to the sump and trying not to incur a frictional power loss. So that's what I'm going to talk about, and the different oil pan designs and the different ways we go about doing that.
One of the things I think about when I look at this is the engines that you're using. Think about this. Most of these were designed back in the 50s.
Exactly.
Okay? So whether they had the windage thought or they knew about it, that probably World War II, you know, they already figured that out. But the bottom line is you got to think where that crank is and position that block. Is it skirted? Is it not skirted? Those are the things that are really kind of tie you in.
The only thing they were concerned with, is making sure the sump never starved and the oil got back to the sump. As far as power and controlling the windage, that never entered their mind. Those engines never turned over 6,500 RPM, for Christ's sake. Well, that's when everything really starts to cost you power, is 6,500. From 6,500 on up, between I'll get into that later because it's going to shock people. But from the worst case scenario to the best case scenario, we're not talking 100, we're talking hundreds of horsepower. So we'll get into that in a second.
Yeah, I'm ready.
From the worst dry sump pan to the best wet sump is hundreds of power.
Really?
Yep.
So we got Bob Mopar, good to see you here. Mark Crawford, good to see you here. So thank you. I just like the idea of minimizing aeration and keeping it available. There you go.
Yeah.
Good point.
Oil control, controlling the oil. And people, well, I want no oil anywhere in the crankcase. That's the perfect case scenario, right?
Yeah. Yeah.
Well, you look at all the pro stock, the comp stuff, the aftermarket stuff, we have sealed cam tunnels. None of the oil from the top drains onto that crank. It's all routed to the front and back. You know, oil routing, oil control, windage control. No matter what pan rail, no matter what engine, that's what you're trying to do. You're trying to balance those things. And sometimes you can't get good windage control. You just have to sacrifice power in order to get good oil control. And in a lot of wet sump pans, that's the case. You really can't start making power or relinquishing some of that friction power until you get dry sump. But I will say that Steph, Moroso, all these oil pan manufacturers over the last 2 decades have went out of their way on these wet sump pans, and I'll show you some pictures of these things, to control as well as route and get some good and release some friction power. And basically, I'm going to be talking about friction power. That's the main thing.
You're on.
So the brake horsepower you see on the dyno is not the total power the engine makes. The indicated horsepower minus the brake horsepower, what you see at the brake, is what the power of the engine actually makes. I mean, if you had a 1,000 horsepower engine, 250 horsepower is just going into that engine's actually making like 1,250 because 250 horsepower is going into accelerating its own components, dragging the rings up and down the bore, the drag on the bearings and everything else. So basically you're taking mathematically the total fuel energy that could be released and then what you're actually getting out the brake. So it's the total power minus the measured power. Now, if you want to go in, all you got to do is Google this. They give all the math, everything. Nobody figures this. Nobody goes into the math on this. This is all done within the dyno. And some people don't even input those variables to do it correctly on the dyno, or don't even. So they just let the dyno calculate it. So basically, if you had to do it correctly, you would take the bore diameter, the ring surface area, the bearing surface area, and all the surface areas and add them up. And it's really complex. But all we have to know is if we do something and it results in more power, like put a thinner oil in there, well, you reduced friction and you got that friction power back. That's what we want to see.
Okay.
So the friction power, the measured horsepower at the crank, minus pumping losses, windage, drag, surface area. Surface area of what? Of the piston skirts, lifters, valve guides, seals, wrist pins, rings, bearings, rocker trunnions, rocker trunk belts, pumps, gears, and anything else that's driven off of that engine. That's friction power. That takes power to move. So 50% of the friction power in an engine comes from the pistons and rings alone. That's why in high NA high RPM engines, you see the ring technology went thinner and thinner and thinner, and the radial has gone from 165 to 140, and we've been able to move the ring up 100 thousandths to make it more reactive. Since you take the radial tension out of the ring, going from 165 to 140, it now becomes a whole gas operated ring. So you have to move it up, expose it to the gas, short gas ports to make it react faster. And it will. Part of the power those small rings give us is from the reaction time, milliseconds. When that pressure acts on the top of the piston, they go out against the bore and seal. Well, if they have less radial tension, the gas can push them out quicker, basically. So we have a reduction. I'll show you how much power there is in the old rings versus the new rings, and it'll shock people. But the piston rings, wrist pins, and skirts of those pistons, if you notice, all the new piston designs are strutted with tiny, tiny skirts. And it's like a Formula One engine has 3/4 of an inch of total surface area on both sides of that piston supporting it, just to reduce down the frictional power loss as much as possible. You wouldn't believe the lengths that they go to. What happens when you take a 15-year-old Pro Stock engine that used to make 1365 using 039 165 rings and incorporate the new rings and new pistons? Okay, so you've changed rings and pistons. You went down to like a 28 thousandths 140 radial from a 39, and you've been able to raise the ring 100 thousandths, which is a ton. Anytime you can raise that ring higher on that piston, its reaction time goes down considerably. So you're sealing the engine up sooner and gaining cylinder pressure that way. And because of less radial tension, the frictional power loss is pretty big. So the billet strutted pistons that we have now versus what this engine had, the surface area of the skirt is probably 1 square inch smaller, which is huge when that piston's going up and down the cylinder 100 times a second or so. So what happens when you do that? It made 1,385 horsepower, 20 horse, in pistons and rings. That's pure friction power. At least 15 of that is pure friction power. Maybe 5 horsepower of that would be the reaction time of the ring. But if you think about it, you went from 39 thousandths, and that ring is a barrel face ring. So it's presenting to the cylinder wall a very small area.
Right.
And all we did was go a little smaller and compact that load-bearing area even more. But we reduced the frictional power loss. Of course, those rings take a completely different hone, cross-hatch, and everything else than those do, because your unit loading's higher, so you need to hold more oil in the bore, and yada, yada, yada. But still, just that tiny little bit is worth a lot of power. And like I said, friction power is hundreds of horsepower it takes for the engine to actually turn itself over. And when you're dragging the rings up and down the bore, you think about that. You're covering a hell of a lot of surface area. And people don't think about the guides, the valve guides too. The valve's going up and down in that guide. That's a lot of surface area. It could take 10 horsepower or more just to move the valves through the guides at RPM. Now, I'm talking about higher RPM engines, 9,000 and above, or let's say 8,500 and above. You're not really going to see a return in friction power concentrating on it a lot below 8,500 RPM, which is one reason you never saw anybody do this, in World War II with lower RPM engines or 60s or 70s. We weren't turning engine speeds high enough to dictate us to redesign everything in order to capitalize on that. Clearances. Okay. I see people say, well, you need this much clearance with not much clearance on this engine and aluminum and iron. And yeah, I get it. And they're stating those clearances because that's what they find works. And that's great. I do the same thing. Everybody does that. This is what I run. That's what it should be. Right?
Right.
So if you have a bit more clearance than necessary, let's say you only need 2.5.
Yeah.
At a minimum, you're trying to push it down. Well, first off, why are you trying to close that clearance down? What is your motivation for doing that? And what is the end result? And is that end result positive? A lot of times it isn't. And in a high RPM engine, clearances are dictated a lot by the distortion of the components than it is the adequate clearance to move enough oil flow to cool the bearing and form the hydrodynamic wedge. So you got to consider that. In low RPM engines, like an LS, yeah, you can get away with 2. You could do that. 2.2, 2.5 would probably be what most consider big. But let's say you have an engine, it has 3. Let's say it has 3.2, 3 2/10. Well, that's too much for that engine. If you have a bit more clearance than necessary, only you're going to know it. But if you have too little, everyone will know it because the engine will see it. I've never seen an instance, not once in my career, where a little bit too much clearance on a bond bearings hurt almost anything. And now we have ring technology to control the oil even more. So, and now we have thinner oils. You have to have more oil flow through the bearing. Clearances are dictated per engine, the intended use, the engine design, the architecture of the crank, the width of the bearings. All that's dictated by the engine that you're working on. In a tiny little Honda, you can have 1.6, and that's fine. If you opened it up to 2, what would happen? Well, the factory engines close the clearances up as much as they can for longevity, so the engine will go 100,000. So if they start off at 3, which would be fine, it's going to end up at 5 by the time 100,000 miles. So that's their reason for running them as tight as they can, and the thinner oils that we have nowadays flow easier, and because it's thinner, you need a higher oil flow to carry the heat from the bearing. Okay. But my point here is every engine is different and every intended use is different. And like on the Pro Stock deal or comp deal or whatever engine, if it's a super high speed NA engine, we will narrow the bearings until they start to burn up and then back off. And that's it. So if you take a big block Chevy and you take 50 thousandths off both sides of those main bearings, you have essentially removed the surface area of one entire bearing out of the engine. And if it takes 5 horsepower per bearing, it just handed you 5 horsepower that goes to the crank to turn the rear wheels. And that's what we did. We did that all the time. You narrow the bearings up until they want to burn up and then back them off. as you can see how narrow some of these bearings are in some of these high-speed engines, it'd probably shock you. Everybody, a lot of people say, well, how much oil pressure do I need? You should never look at it that way. You should never look at pressure as a problem unless you don't have enough. Because high pressure can mean inadequate flow. Okay, so pressure and flow are not independent. They're somewhat related, but they're not proportional to each other. So if you want high pressure, you can block off every bearing and you'll have all the pressure in the world, but no flow. And low flow can mean inadequate clearance or low pressure. And low pressure can mean too much clearance or high flow. So that's why the NASCAR guys dyno their oil systems. They know the flow in every channel of that engine. They know exactly how much pressure drop, volume drop there is going around a galley and coming down the other side. Because they have friction dynos. They do this. So basically in drag racing, what we're doing is we're just trying to reduce the oil pressure to reduce friction power losses. Because let's say you're turning the pump twice as much as you need, twice the RPM that's needed, well, you're just bypassing oil, and every bit of oil you're bypassing is costing you power. So in high-speed engines, what we'll do is lower the RPM of that pump just to the point where at low RPMs it's bypassing, and when it gets to the top, it's bypassing almost nothing, which is a balance. You want to bypass as little as possible. The other thing is an efficient oiling system. There has been people who have extrude honed the oil passages. And I saw a test on this. And it was, who's going to go to the extremes of extrude honing the oil galleys and getting all the rough edges and stuff of them? Well, this engine at 10,200 RPM required 52 pounds of pressure to move X amount of volume through the system. And after that was done, it took 48. Just a reduction in head pressure due to the oil galley being more efficient flowing through it. NASCAR guys are really big into that. Those engines, they take a lot of effort to make sure that that whole system has the lowest friction power as possible. Oh, I forgot I did this. It was 56 PSI, I dropped to 48.
Okay.
So if you think about it, you have an oil galley and they're drilled 90 degrees, where you have a sharp edge there. And every sharp edge takes about 10% more pressure for every one that goes around there to maintain the flow. Well, if you radius all those edges, the head pressure can drop and the oil flow can maintain or go higher. Same with an intake port. You know, if it comes in 90 degrees, you could lay it back and the flow comes up. Well, friction power in springs. If you could really know how much heat a spring generates, it would probably shock you, especially like a triple. And I'm going to take a triple spring. Those coils have to interfere with each other. They have to rub against each other really, really hard. And that causes a lot of friction. Well, why do they do that? Because each spring has a resonant frequency. And if you rub them against each other, it will cancel that. So they won't vibrate and go nuts at some individual RPM where they might encounter that. So what the NASCAR guys do, and I do, and a lot of people do, is we'll actually submerge the springs in oil, especially the exhaust. You want half the spring submerged in oil, and that will do two things. It will reduce friction power. It will reduce the harmonics. It'll let the vibration of the spring go out in the oil, and let's see what I have there. Take a spring, take any spring, any triple spring on a spring tester, and super glue a temperature probe to the outside coil, and just sit there and cycle it 60 times and watch the temperature go up a couple degrees. Now think about cycling that thing 60 times a second or 80 times a second, like in really high-speed engines. 80 times a second. This is narrowing bearings. For a given area, at some point the load will overcome the surface's ability to maintain a hydrodynamic wedge. In other words, a bearing acts like a surfboarder at a beach. When you run and jump on a board and it skims across, okay, that's how a bearing actually functions. It's a hydrodynamic wedge. Well, once the pressure gets so high, it will break that oil down and the surfaces will touch. The unit area, the area, the width of the bearing, and the width of the main, and that area across there dictates how much load it'll take before that happens. So the friction power in some areas can be quite high, and the parts wear characteristics will show it. Okay? And by show it, it'll show galling, it'll wear, let's say you coat it, it'll wear the coating off real quick. And this is why when a racing engine comes in, the engine builder or the teardown guy, when you tear an engine down, it tells you a story. You look at all the wear patterns on the engine, and you can tell if it's happy or not, basically. And I'm going to show you an instance where we all knew, all the engine builders back 95, 6 knew this. We saw it, but we couldn't do anything about it. Jessel had if you look at the Jessel keyway lifters now, they're a lot taller than when they first came out. They were really short. So they broke down, they didn't last very long. We had to replace them a lot. And they would wear out the lifter bores, and they would wear out the outside, the tips and the bottom of the lifter from cocking it and side loading it in that bore. And it was like really self-evident. I mean, it was so bad that it knocked 3,000s out of a bore within, 50, 60 runs. You were replacing lifters all the time. So, dang.
Timed out.
I hate this. I'm going to get a new camera. This is pissing me off. Okay. So, we saw it. We knew that it was wearing horribly. The unit loading at those points has got to be ridiculously high.
Oh, yeah.
So, the short body lifter, now this is the short body, but the short body lifter was 200,000, 250,000 shorter than that, the current short body. And now we've gone bigger diameter and even taller because of what I'm about to show you or tell you about. A certain engine builder called me and he said, I did a test and then I went back and I put it back the way it was because I couldn't believe what I was seeing. And then I put it back and it made the same power. And then I put it back again just to make sure
Jesus,
the amount of power I was seeing was actually what I was seeing because it was ridiculous. But if we think about it now, it's not ridiculous. It's just then we didn't understand how much friction power those lifters were costing us. On an 800 cubic inch motor with 250 gross lift. Now you got to remember, Pro Stocker back then was about 990, 980. This was an IHRA Pro Stock engine, turned 8,500. So we were knocking lifters out all the time. He was knocking them out twice as fast because he had so much more lift. And when he called me, he thought, this thing made 15 more horsepower? That's insane. For 220 thousandths of lifter, cost me 15 horsepower in friction. He couldn't believe it was that much, and neither could I, really. Well, that guy was John Causey. He did this test multiple times because it's amazing that little bit, and it was because they were way too short. They were cocking in the bore so bad.
Okay.
And you could see it in the wear, but at the time it was like, what do we do? Call up the manufacturer and tell them how to design it? We didn't know any better either. So we should have picked up on it. They did. Somebody did. So the point I'm trying to make is, if you're in a range, let's say you have a lifter that tall that costs you 40 horsepower at 9,000 to turn over, and you start shortening it, you're not going to see anything until you hit that one point where the unit loadings just goes out of control, just like a bearing. You start narrowing it, and the unit loading's going to hit a point where it can no longer maintain a hydrodynamic wedge, and they mate and burn up. So when you're designing two parts that rub together, the frictional power loss is something you take into account.
Now, is that 15 horsepower per lifter?
No, total.
Okay.
Total. Yeah.
I was like, what? No way.
So, windage pans, scrapers, there's a lot of ways to counteract the problems. In an engine, a non-skirted block, at about 6,000 RPM, the oil coming off the crank is pointed down about 6, 7 o'clock coming off that crank. And then it goes 7, 8, 9, and by 9,000, it's vertical. It's trying to come off directly off the crank. So depending on where you put louvers, reliefs, see, these aren't scrapers, these are reliefs. This allows the engine, the oil that's already on that wall, to go this way. So it's not costing you power. A scraper costs you power. If you stuck a blade up there to rip the oil off of the crankshaft, it would cost you 10 to 15 horsepower. So the idea is to route the oil, get it off the crank. Don't let the crank pick it up and turn it around, and keep it wrapped up around the crank. And you notice there's no scraper on the kick out side. All the oil wants to go this way, but there's no scrapers there to rip it. All it's trying to do is just route the oil. This is a wet sump pan. This is a completely different design criteria than a wet sump. Have you ever seen these blades right here in an oil pan?
No.
Remember when I told you that the JC51 was segmented?
Yes.
That each 2 cylinders was a different sump stage?
Yep.
Well, that's what they're doing. They're not letting the oil go front to back. They're trying to control the oil for every 2 cylinders and treat each individual section as its own oiling system. And we'll get into that here in a second. But what you don't see is any scrapers sticking out. Scrapers cost power. But there's always a but, right? There's always a caveat.
Sure.
Sometimes they're needed. Sometimes you can't route the oil back to the sump sufficiently to feed it during deceleration or acceleration, or what have you, or it keeps too much oil up there and you have to run too much oil in the engine, well, the scraper at that point, it costs you power, but it saves the engine. So,
okay.
This is a Formula One oil pan. It's not an oil pan. The main web and everything and the pan itself is one unit. And there are units that bolt in here. That's the sump hole right there.
Yeah.
Everywhere right there. When the crank comes around, it sees, the crank throat comes around, it sees a little scoop right here. And there's air constantly flowing. So what they do is you should have a certain amount of crankcase negative pressure in order to make the engine function correctly. But you also need airflow in these. So basically they have a controlled leak that balances the negative crankcase pressure and the amount of air going through to control that oil flow. Because the crank is right up against that. The crank throws are real close. So they literally have to have a system that rips it off. And this is probably one of the most efficient types of oiling systems that there is. And here's another picture of another person that has done this. And I don't know what engine this is, but you can see that they've incorporated each sump stage,
yeah,
like that, and routed it back around the pan. That's a sucker pan. That literally rips the oil off. And here's another. I don't know what this is for. I saw this. I'm like, oh, that is a cool idea, because you've got your crankshaft counterweight coming right through there. I mean, it's going to rip every bit of it off. That's perfect. That actually encompasses the whole counterweight as it comes around. We'll get back into clearances, but friction power, again, if you run a thicker engine. Oh, by the way, Lake Speed, and I forget his name, did some tests lately on different viscosities of oil, different, a whole bunch of different stuff. But basically, the thicker oil was not better. Because people forget that oil carries heat. Oil flow carries heat. So you have to have a certain amount of oil flow past the bearing to carry the heat away. So if you close your clearances too tight, sometimes it's not a problem with oil flow. Sometimes it's just a problem with the fact you broke the oil down because you heated it up too much. So if you give it more clearance and get more oil flow, you'll carry the heat away from the bearing. Basically, I'm always saying, don't shove your clearances down. There's no use for it in a drag motor, especially. I mean, there's just no use for it. I tell this story that, yeah, you're trying to get the piston, the head clearance tight. So you don't want those stack tolerances. You don't want a lot of clearance in the wrist pin. You don't want a lot of clearance in the main bearing or the rod bearing, because that's going to increase that piston, the head clearance at higher engine speeds. But then again, now you're narrowing the bearings, the unit loading goes up, you need a higher oil flow, so you're going to have to open them back up. So just accept it. Just say, okay, I got to run 3 on the mains, 3 on the rods, and whatever on the wrist pin, and that's where you got to live. Trying to shrink them down in order to reduce P to V or P to piston to head or something like that is, I think, a fool's errand in my personal opinion. Just give them enough and let it eat. Don't worry about it. Extreme cases. There are extreme cases. And one of the extreme cases was David Raro. He used to tell the story about one of their engine builders that put in one of their high RPM small blocks. It turned about 9,500. Well, this engine came back in, and the teardown guy was like, David, you got to come here and see this. I'm not seeing what I think I'm seeing, am I? And the thing had 10 over bearings on a standard crank. So it had 13 thousandths bearing clearance. It ran for a year and a half and won the championship. Now, granted, it was a different time, okay? Those engines weren't as critical as they are now, but point in case, too much isn't going to hurt you. You might overload the oil rings and the pistons. Yeah, you might get a little more oil past the piston. Yeah. But as far as burning up, no, too much will never hurt you there. So when it comes to bearing clearances, I'm always the guy that says, just give it a little more than it needs and let it eat and don't worry about it. But sometimes you have to open up the clearances over and above what you would even think was normal because the component distortion. The pistons may distort the wrist pins. In Pro Stock, back in 8, 9, we had problems. We were pulling 23 inches of crankcase pressure, negative pressure, and we were robbing the wrist pins of oil. We killed all the oil mist. The wrist pins couldn't get oil. So consequently, they would beat themselves out. They got just enough oil. They maintained lubricity that they never seized, but they would beat the wrist pin out 3 thousandths, from like 1.6 to 3. And my brother beat his brains out about that over and went to a 1030 pan and back down to a 990 and, played with the surface area and was still doing it. Now, you have to remember that's not as much of a problem it is now. We have better alloys for the pistons. We have better piston designs that you don't have to incur this problem. But this was a problem that we faced back then. So every time you take the damn engine apart, it was 3.2 thousandths. They'd beat it up. They'd oval it top to bottom. So my brother just went, well, screw it. Give it 3. Let it eat. Fixed it. The engine told us what it wanted. Just give it to it.
Yeah.
Back then, that was the fix. That's not the fix now, but back then it was. So, if you have components that are hitting, smacking, wearing, touching, maybe, just maybe, you give it a little more clearance and it goes away. That happens a lot. Point in case, the LS crankshaft. The LS crankshaft does not have center counterweights. This is a Dart LS crank. Richard Maskin went out of his way to get these made, and this fixed so many problems. Like a super stocker, I think they're allowed to use center weight counter cranks. I'm not sure. I'd have to check the rules. I know they were trying to update it, but the super stock LS engines had to use the non-center weight counted crank. Well, why do you need center counterweights? Multiple reasons, but the end result is when you have this much weight on each end of the crank, it has another moment and it will set up an oscillation. So the center main, instead of running true, is doing this constantly. So on each end of that bearing, it will wear it all the way to the brass, because that main is sitting there and going in an elliptical like this, and around and around and around. So the outer 50 thousandths on both sides of that main bearing, that center main, will go right to the brass. It'll just eat it up. So you give it more clearance, right? And then it doesn't eat it up. But more clearance requires more oil flow. And this is a full skirted block, which is already the epitome of the worst oil control period. Now you're having to flow more. And the bearings on an LS are too narrow. The unit loading is already too high. The oiling system is, well, I'll be nice. It's not very good. So a superstarter has to run 120 psi of pressure and try to run enough oil so the sump won't starve, and mess with all these louvers and everything else to try to get the oil flow correct. But you put this one in there, your bearings shrink up, your oil pressure drops to 65 pounds. You can turn it to 9,500 and not hurt a thing. You know, and the non-center weight counter deal, that really starts to come into effect about 8,500. By 9,000, it's hurting. That crank is jelly, man. It's going all over the place. And likewise, it makes it worse with a stroker crank. And it makes it 5 times worse when you heavy metal balance it, because the only place you're going to put heavy metal is on the ends. And now you have these 2 weights out here that want to go like this and this. So you have 2 moments on a non-center weight counter that you don't have on this. This thing will not oscillate. And you could make a non-center counterweight crank oscillate like that. Just put too much heavy metal on the outside edges and it'll do it. It'll set that moment up. It'll happen. So when you heavy metal balance a crank, you have to displace the metal throughout those counterweights. Otherwise, you could end up with that. So they started making stroker LS cranks, which just compounds this problem. And it takes the RPM range in which those problems really start to matter down about 1,000 RPM, which is not that bad because stroker engines don't have to wind up that much. So a lot of people didn't see those problems in engines that only had to turn 7,500. Then you start getting into racing cranks that you try to make them as ultralight as you can. The friction power, reduce the friction power, reduce that moment of inertia, the acceleration. The friction power, part of the friction power in an accelerative state, when you're accelerating the engine up, is accelerating the mass of the components. The crankshaft, the rods, the pistons, the whole reciprocating, rotating mass must accelerate, and that takes power away. It's easy to see if you haven't set the inertia factor on your dyno, which 90% of the people don't. You can make a static pull on the engine and then accelerate it at 600 RPMs per second and then accelerate it at 1,000 RPMs per second like you do in first gear, and you'll see 20 horsepower less because you're using that 20 horsepower to accelerate the internal components and overcome the increasing friction from the rings and everything else trying to accelerate it. So they go to a great extent, undercut counterweights, center drilled. You know, that doesn't mean a lot. The closer you get to center, the weight doesn't have as much effect. The farther you get away, that moment of inertia skyrockets, and it gets harder and harder to accelerate something that's a larger diameter, because that weight means, it's like when you look at a speed skater, the conservation of angular momentum, they pull their arms in, they speed up, right?
Right.
See, even in these are scalloped. I think this is like a windbird. You notice these are shaped, every throw is shaped like a wing to cut through the oil.
Yeah.
And then you have like parkerizing and coatings, oil shed coatings. Yeah, that's worth power, friction power. All that oil that goes around that crank it has a boundary layer condition, it has a viscosity, it's trying to attach itself. And that throw right there has to bust its way through. That's just power. It takes power to do that. It's friction power. So anything you can do on that crank to reduce the force it takes to move through the oil, it's free power. And one of the things that we did and never talked about, ever, was on like a Pro Stocker back in 2000, 2006, we would take the cranks and just shove a ton of heavy metal into them, and then cut the counterweights down as much as we could. Heavy metal, you can see the heavy metal right there. See if I can, there we go. There's the heavy metal right there that's in the counter.
Yeah.
Well, you'd have that whole thing full of heavy metal in every counterweight, and then you cut the counterweights down. I think we got about almost 1/4 inch in diameter off of the crankshaft. Now, how much power do you think that's worth?
15
6 horsepower on the average.
Wow. Wow.
Well, that was also in conjunction with the fact that we went down in overbalance, because a standard overbalance is 50%. So we went to 46. Now you could go to 45. Well, let me explain this. At 46, the engine would tune up between 7,500 and 10 grand. Below that, it would shake like a nervous hunting dog. It would just sit there, and you could even feel it in the handle. And you'd walk into the handle, and it would just go boom and clean up as soon as it hit that RPM. So what that allowed you to do was decrease the counterweight diameter. That's going to extremes. Nobody's going to do that unless you're looking for that last 2 or 3 or 4. Now here's a crank that's been super metal balanced. You can see that every throw has got heavy metal in it. Now, if this isn't done properly, this will kill somebody. I've seen it happen twice, not kill somebody. I've seen these let go twice. Yeah. Because if you notice the amount of area, oh damn it, let me see if I can blow that up. The amount of area I can't blow it up. Right there.
Couple thousands.
Yeah. You think about that. All that's holding that is that area right there. That's all that's holding that. So if those fly apart, a shotgun slug, those are like twice the energy of a shotgun slug at 1,250 feet per second. If you're going to throw that out of there at 9 grand, that'll go through anything. And that's tungsten. That stuff don't distort. As a matter of fact, the Germans, when they ran out of a lot of metals, were starting to make tungsten rounds out of tungsten.
Really?
That's where the armor-piercing round came through, because they realized that it would go through just about anything.
Yeah.
Now here's an ultra light crank, and even the center counterweights are just blades sticking out there, just enough to have that engine in balance at the RPM range that it operates in. Everything is drilled. Everything is scalloped. Hold on a second. See if I can get it. There we go. Right under there, it's scalloped.
Yeah.
Every weight that can be taken out is taken out. Now, here's the catch. That thing on either side of the power band could be a bit of a shaker, but that's not a problem. The main problem with taking cranks and starting to lighten, you're going to hit a point where the torsional is no longer structurally rigid enough to transfer the power to the crankshaft without incurring another moment or flex or twist. And that friction power, you're increasing your friction power because of the distortion of the crank. And then that would lead you to have to open the bearing clearances because they're hitting on the main bearings, So there is a point where reducing the weight will bite you. And I've seen it in blocks too, a lot. If you lighten a block too much, boom, man, you can kill 10 horsepower, gone. You'll never get it back. We did that twice. We had LSM do a lightning program on a block one time, and we thought the engine made about 2 horsepower less. It's hard to quantify that level, but it's like, man, I know that block is not making the power it did. And we had another one, and they were doing what they called an ultralight program on that one. That was 8 horsepower off compared to what it was. We just wheeled that out the back door. And everybody talks about 180-degree cranks. Yeah. Well, one of the reasons, the main reason, I mean, they have balancing issues, but they're so light. They're so light. There's no mass at all. I mean, they rev instantly. So if the acceleration component of the engine, if you took a standard crank and I don't know the actual value, and one of these cranks and did an acceleration pull, that thing's got to be worth probably 10 horse at least, if you can overcome the balance issues and other things associated with them. But for low RPM engines, like in the Mustangs and stuff, that's fine. High RPM, not so much. What's the total power loss from windage? With the best oil pan and sump design, a dry sump design, how much power is left by redesigning or refining the design you have in front of you? How would you tell that? It's like, okay, well, I tried this pan and it's worth 4. How much is left? What design do I have to do in order to extract more power? And is there a design that can extract more power? How much is left? Is there 10 left, 20 left, 40 left? How do you quantify that? Well, David Rear and Buddy Morrison decided that that's exactly what they were going to do. They were going to quantify the total friction power from a pan. How do you do that? Put a pro stock engine on the dyno, remove the oil pan, stick oil pump in a 55-gallon drum of oil, make a dyno pull. Spend next 3 days cleaning oil off the walls of the dyno room. That's how you do it. You remove the oil pan. Ta-da. That's 100% efficient.
Yeah.
Right?
Yeah.
So now you have a quantified 100%. Here we are, and we're here. Now we know how much is left. Now we know not where we have to go to work, but we know that the work we're about to do, we could capitalize on some of that. That's important to know that it's like working on a port. Well, how much is left? You have to know that. So how much, everybody out there right now, write down how much power do you think a pro stock engine at 9,500 RPM would gain by taking the oil pan off? Put it in the comments because I'm curious. I'll wait.
I'll tell you.
Don't go crazy, but
I see people already starting to put some stuff down.
What are they saying?
Let me see if I can scroll up. Like one guy says, Greg, I'll read their names too, because people like to hear their name on there, and I like to say it. Wow, they're coming in. Greg Ertman says 52. Ricky's House of Crap says 5. Turbo's Welding and Repair, 33. Novaman, 50. Racer Bob, 15. Ryan Carmichael, 40. Vic Bloomer, 80. Jason Bello, 40. 43. I'll tell you what Warren Johnson told me when I showed him that picture that I was putting up there. He said, what? Tim, why the hell are you even bothering with wet sump pans? Stop all that nonsense. Put a dry sump on it. You're going to pick up 35 horsepower right now.
35 to 45.
That's what he told me. He said, stop messing around with that. So that was about 2 weeks ago. We were talking about this.
Okay. Well, I'm glad you brought that up. Let's put this in context. Before I tell you how much taking off a well-designed dry sump system at the time,
yeah,
we know from tons of experience that converting a wet sump to a dry sump is 35 to 40 horsepower. And I've seen 60. Jesus. Well, it's not that the dry sump was that good, it's that the wet sump is just that damn bad.
Got it.
And so we know that, just call it 35 horse.
Yeah.
Taking the oil pan off of this engine was worth 110 horsepower.
Jesus. I think the highest guy up here was Vic Bloomer at 80. Another guy, Bob Mopar, said 80. Some people said as low as 3.
Oh, it shocked the hell out of everybody.
Wow. Yeah.
We had no concept, just as this audience has no concept. Yeah. Well, of course we don't. You don't know it until you try it.
Right.
Well, 110 is like, no.
Yeah, I couldn't believe it.
So it's like, okay, we gained 35 going from a wet sump to a dry sump. And taking the dry sump off back then was worth 110. It's not worth 110 now because we've advanced.
Sure.
We have better oil pumps, like the dailies take, 10 horsepower less. We've got better oil pans, a lot better oil pan designs, better crankshaft designs, better block designs, which I'll get into. So basically now it's probably about 60. We've extracted that much more out.
Right.
So my old man used to call it mouse ounces. Okay.
Yeah.
It's doing all those little things that everybody thinks are insignificant and take too much time to do. But if you do all of them, you make 100 more horsepower. I'm not shitting you.
Yeah.
I'm not embellishing. I'm just telling you, professional engine builders know that if you concentrate on the fine details, you can extract a ton more power out of an engine. And I can't count how many times I gave cylinder heads and intake manifolds camshaft to somebody, and they were 80 to 100 horsepower off. Because they didn't know or concentrate on all the little things that add up and work together to create more power.
Right.
So, windage in a crankcase. Now, we knew that there was 110 more left. So then we start polishing cranks. Then you start bullet nosing. Then you start shaping the throws like a wing, and you start removing all the edges, every lump, every ridge possible in that crankcase. I've spent 2 days polishing a crankcase for less than a half a horsepower. But if you do everything, it'll hand you 10 horsepower. Half horsepower here, half horsepower over there, one over there, quarter over there. It's a lot of power. Also, if you epoxy and fill the ridges, if your crankcase isn't shaped properly, shape it properly yourself. Go in there with epoxy and reshape that damn thing. Do it all the time. And I mean, just on a Mopar, we'll get into full skirted blocks here in a second, but that's a disaster. It's a disaster of controlling oil. So anything you can do is going to pay big dividends. Where if you had a system that was already efficient and you did all those little things, it's going to be 1 or 2, where on a Hemi it's worth 5 and 6 and 2 and 4 horsepower. And what you do in the back of the block and everywhere there's a ridge or a problem, you just fill it in with epoxy and shape it till the oil shoots off. I'll show you that here in a minute. Also, the pan rails in the direction of the kick out. And by the way, you can never have a big enough kick out. You can't run a big enough kick out on any oil pan, it won't fit in the car. If I had a kick out that's 2 foot, awesome. You ain't going to fit that in anything.
No.
But you're confined to the intended use, so the design that you're working with has to fit, whether it's a rail or a 66 Hemi car, which is a disaster when it comes to oil routing, control, windage. It's a full skirted block, and the control arm goes through the oil pan and a big hole. So it's a disaster from every aspect. But that means that the gains are bigger for anything that you can cure. I'll show you that here in a minute. Which is also on standard V8s, non-skirted V8s, every manufacturer out there and every engine builder goes to painstaking efforts to make it as wide as possible. Why do we do that? Why the new Ford Eliminator blocks or any of the new blocks that come out advertise wide pan room? I'll show you. Okay, now I know this is a 2-bolt block, but let's take the worst case scenario and maybe see these ridges right here?
Yeah.
Radius those off. Is it worth any power? Probably 1/10 of a horsepower maybe. But in oil routing, getting the oil off the crank, it pays pretty good dividends. The main caps, 4-bolt caps, they're like this. On a Pro Stock engine are like this. They're cut at an angle. You cut both of those sides in to reduce the drag. So when the throw goes by, it's seen in increasing area and lets go of the oil instead of dragging it along the side of the main. So we reduce this width there.
Yeah.
And see all these little ridges right there? Let's see if I can blow this up. Nah, it's already too big. These little ridges right there.
At the bottom of the cylinder, you're saying?
Yeah, all this.
Yeah.
Look at this. These look right there.
Yep.
I'll go in and grind them and put a radius there. And just that little ridge, removing all those ridges, could be worth 1/10 of a horsepower. And then you go in there and remove all those, and that's another 10. Pretty soon you got a 1/2 to 1 horsepower. And then you polish the whole crankcase, and then you fill all these areas, these dead areas in where the oil can get up under there, fill them in with epoxy, and make it a straight wall so the oil can shed off the crank. Pretty soon, 2 days worth of effort of polishing and grinding is worth 2.5 to 5 horsepower. Now, who's going to go to that effort for a general bracket engine? Probably nobody. But if you're in a competitive class, yeah, you're going to do it. The Hemi and other engines have a huge cavity back here that traps oil. Fill it in with epoxy. You fill it in, and then what's really cool is you can take a brass tube from the top and route that oil through the epoxy and down right there and dump it away from the counterweight, so you're not having all the oil from the top of the engine dump onto the crankshaft, pick back up, and increase your friction power. Oil routing. On a wet sump, it's worth a lot. Sealed cam tunnel. How much is a sealed cam tunnel worth? It's 4.5 horsepower at 10 grand. So you add up everything we do in the crankcase with the crankshaft, the cam tunnels, and everything else to reduce that friction power, it's about 20 horsepower. I'm not giving up 20 horsepower.
No way.
People keep asking me, well, how do these engines make so much power? Because everybody concentrates on the details. Details nobody else even thinks about. But this is the name of the game. Every tiny, teeny, tiny little ounce of horsepower I can get, I'm going to get it. No matter how much time it takes me to get it. If it takes me 10 days to grind this thing and polish it out and remove everything, that's what I'm going to do. Now, that's a highly competitive class. Not everybody's going to do that. people think, well, the heads and the manifold and the engine design that's what makes 2.9 horsepower per cubic inch. Okay, well, you have to have a good base, but it's all these small things that add up that make that much power. And I always show the graph of, I should have put that in here. You know what? To make 2.2 horsepower per cubic inch, the graph would look like.
Oh yeah, I remember.
Look like that, you know.
Yep.
And then by the time you hit 3 horsepower per cubic inch, you're there. So you could be off on friction power, manifolding, camming, and everything else quite a bit, but up there, you can't be off anything. And this is a culmination of mouse ounces, all those little teeny tiny things that people don't concentrate on. And it's like I always say, if you want to win races and championships, you have to do what others are willing to do or unable to do or don't know how to do. And one of those things is just concentrating on all the teeny tiny little details. And it's amazing when somebody doesn't do it and you see, well, I made 50 horsepower less. Well, that's because you didn't do everything we did. Why do aftermarket manufacturers make the pan rails wider? Why do they advertise this fact? This is an advantage, but why is it an advantage? Why do aftermarket manufacturers why don't they redesign non-skirted blocks into full skirted blocks? If they're so much better, they're so much stronger, why don't we use them? Why has that never happened? Not once has anyone taken a non-skirted block and redesigned it into a full skirted block.
Because it's not better.
It's not better. It's freaking horrific.
Right.
The Dart block. This is the Dart LS Next. Now, when Maskin was designing this block, I was talking to him one day and he says, guess what I'm going to do? I'm going to design this block non-skirted. And I was like, thank God. Thank God. we have 40 horsepower. That's what it's worth. You try to wind up a full skirted block, there is no such thing as adequate oil control. The oil just stays on the crankshaft. And then you have to employ scrapers and pans and all that crap that costs you friction power. This is 40 horsepower at 9,500. 50 to 60 horsepower at 10 grand. This is why I hate full skirted blocks. I always tell this story. When Larry Morgan went to Mopar and Pro Stock, all they had was full skirted blocks.
Yeah.
So he put one on the dyno and he was just dismayed. He was 68 horsepower down. And it's just like, wait a minute. This is insane. And beaten. It was a full skirted block. Couldn't get rid of the oil. Had to run oil. It was a mess, of course. Any full skirted block is a full scale disaster from an oil control and windage standpoint. And the funny thing is they sell this block. Anybody can buy it, but they had to make an adapter kit to turn it into a full scale or a skirted block because people wanted it because they didn't know any better.
Huh.
And I see that all the time. And what's funny is he told me before he passed that they're selling the skirted blocks 10 to 1. It's just what people know. They don't know any better, and that's what they know, so that's what they buy. You will never see an unlimited NA engine that makes a ton of power with a full skirted block. You see them in supercharged applications, top alcohol, funny car, and stuff like that. Are they stronger? Yeah, in certain configurations, they're a lot stronger. We don't need that strength. And we're not making 5, 6, 10,000 horsepower. We don't need it. As a matter of fact, we could put aluminum main caps on our Pro Stock shit. That's how much stress we're putting up with. I mean, 1,500 horsepower is not a lot to have to handle. But when you get up to 2,500, 3,000, okay, yeah, you could still use the non-skirted block. That's fine. 3,500 horsepower, that's not a problem for an unskirted block. 4,000, no, I don't think that would be a problem either. But once you get past 5,000, it might be a problem. Might be stronger. Might be better to go to a full skirted block. The 30 horsepower loss I have here is at 8,000 RPM. Now, as engine speed increases, the loss increases not proportionally, because you can go from 8,000 to 9,000 and it'll be 10 horsepower, and you go 9 to 10, it'll be 20 more, and 10 to 11 would be 30 more. It probably would not be controllable at that engine. It wouldn't be controllable at that engine speed. You couldn't control the oil flow and windage at that engine speed with a full skirted block. I don't really think you could. So Larry Morgan saw that he was making 60 horsepower less. He knew, he'd been around long enough to know a full skirted block is a disaster. And he was cutting holes in the side of the block between the mains, trying to make sump systems in there to suck the oil off the crankshaft. He got 40 of it back, but you can't be 20 horsepower down in a Pro Stock deal. You ain't even qualify. So I think they redesigned the blocks for him. I'm not sure. I'll have to ask him, but I'm pretty sure that they did. And by the way, the LS engine, I don't talk about it like at all. It has all the valve area, cylinder head that is needed to make 800 horsepower really easy. What I don't understand, and I have never been able to even rationalize, is why they tried to make a 427 side oiler, oiling system and full skirted block, and then put it into a modern engine. I don't understand. I don't. Questions?
Blocks that are full skirted. Ford FE blocks, like you said, the 427 Siler, 390, all of them, they're full skirted. The Hemi is. What other blocks are? Like, is Pontiac? I don't even know what they look like on the bottom end.
No, Pontiac's non-skirted.
Okay. Here's a comment right here that just speaking of what you're talking about. James Miller said, I've seen a full skirted block with the windows on the passenger side to let the oil fling out, and then a special pan to catch the oil. Just what you're talking about.
Yeah. That's probably handed that guy 30 horsepower in a wet sample application.
Yep, you're right, Robert Bray. Cleveland's aren't skirted. Here's another good one right here. Then you got cheap-ass customers that don't want to spend money on a good oil pan.
Yeah, because they don't understand the importance. I mean, engine builders are always fighting. We know what to do. We know what should be done. We know all the little mouse ounces and all the things we work at to build power. It's just very few people are willing to pay for that. And we make it look easy. Engine builders, professional engine, all of us, we make it look easy to our customers. So they don't understand in their head the money they're spending and the work involved, which is why I started the induction system training course in the first place. At Rare Morrison, David said, hey, why don't we had customers that were coming in that were baby boomers, that were wealthy, that raced in the 60s, that wanted to pick it back up. Well, they weren't up on new tech. you know, and as far as setting valves, as far as, you know, looking at air fuel ratios and stuff like that, they were clueless. So he says, we need to have a school to train our students. And he says, more importantly, it shows them, we can walk them through this and show them the amount of work and how much work and what we concentrate on. And it will give them a better perspective of the money they spend, to show them the amount of work that we do and what all goes into building their race engine. And that's how the Rear Morrison Race Engine School started, was educating our customers. And then it just exploded. Pretty soon we were doing classes every 2 weeks at every Ford and GM plant in the nation. I mean, it was amazing. And then GM made it mandatory for their engineers, their new engineers, to take it. Not that we were going to teach them any new engineering schools. It's just, when you have a new engineer that comes out of school, he's clueless about what he's doing and designing. As anybody, I don't care if you're the first guy sweeping floors as a janitor, you don't know how to sweep the floors properly until somebody shows you. It's the same thing. When you come out of college as an engineer, and I have 2 brothers that are electrical engineers, you're a babe, man. You are greener than newborn grass. You don't know jack. And it takes 10 years to learn. So we just showed them, hey, listen, this is what we do and why we do it. So now you can go back when you're designing those ports, you can think about all the aspects, what we think about.
All right, here we go. You ready? Nova Man, is a 440 Mopar skirted? I think so.
Yeah.
This is a good one. Jeff Ott, will a drop in oil pressure from a vacuum pump equal some power?
Okay. Double-edged sword, and you're playing with fire.
Yep.
When you start increasing your vacuum to the point where you see a drop in pressure, you're playing with fire. You shouldn't ever see that. You never want to increase crankcase negative pressure to the point where it affects the oil pump, even close. Because if you're at that stage and something happens to that sump where it gets a little clogged or something, boom, rod's right out the side. You cannot do that. And that's why we put a 10-inch vacuum limit on all wet sump. Can you pull 15? On some, yeah. On others, boom, right out the side. So a 10-inch, that's fine. Just about all of them can pull 12, whether it's full a Mopar or a Chevy, a Ford or whatever. So we set the limit at 10. And that's why you have those pressure reliefs, especially for a wet sump, you set them at 10 inches, and it's safe. At any point where that vacuum starts to affect that pump, it's dangerous.
Now, Johnson told me last week that they were running, I think he told me they were running 23 inches vacuum, 24.
I mean, we routinely ran 22, but you need as much as you can. You get all you can get.
Yep.
That's what you do. And the more efficient you can make that oiling system, and again, just like a wet sump, you're balancing the pump, trying to pull the oil out, with it trying to pull the air out too. So it's tugging, it's working itself. So there's a point where everything tunes up, what they call the Q, where everything balances, where you're not trying to use so much energy trying to pull the vacuum down that it's actually costing you power.
Or engine parts. Tom Hamilton, thanks for the updates. We appreciate you being here, Tom. Any preference between a screen or a louvered metal tray?
No preference. Each one has its place, and in which engine it works better, I or no one else can tell you unless they've tried it and done it and R&D'd it themselves.
Then try it again.
I've tried 2 louvers, 10 louvers. We had movable louvers. We have escalating louvers. We've done all that decades ago. And the screen is like, okay, the screen will get just about 75-80% of everything you get. Now, if you go to a louver, you're going to get that extra little. But in most cases, it's probably not worth playing with because you're going to have to get on the dyno and really play with it. But I like the Scream because it's simple. It's dirt simple.
Yep.
And you're going to get most of it with the screen anyway.
Mike G, thanks for being here. You mentioned aluminum main caps. Can you speak to iron versus billet steel caps? When, if ever, is a steel cap needed?
A steel cap is really always needed. You always need a steel cap. Can you push the limits by using aluminum cap? Yeah, in a lot of cases you can. And it all depends on
RPM.
Depends on a lot of things.
Yeah.
So, I mean, we tried aluminum caps in pro stock engines and got away from them because they just don't have the structural rigidity. In some engines, you can get away with it. Some engines, you can't. And I really can't say any more than that. Now, me, I would never use an aluminum cap on anything unless you're trying to scrape out that last bit of weight. And I've seen that happen in pro stock. I even saw it happen in pro mod. There was guys trying to run aluminum caps to save that 5 pounds.
Yeah.
But let's look at it in the big picture. That 5 pounds is below your instant center, way below it. It's not going to have that much effect on the weight transition of the car. 5 pounds is what? A couple thousandths of a second? I'm not going to do that because that's the highly stressed area in the entire engine.
Right.
And that's not the place, in my personal opinion, to save 5 pounds.
Bob Mopar, we've talked about this before. When is a crank scraper a good idea? Application.
When you can't control the oil. When you shove the brakes on and all the oil's wrapped up around the crank and the oil pressure drops. When you can't control the oil in acceleration, in an accelerative or decelerative state, or a round deal where all the oil goes to the side. If you have an oil pan that's not designed properly to withstand those dynamics, then yeah, you got to use a scraper. You got to cost yourself power in order to save the engine.
Tim Hilliard, Optimum Performance, thanks for being here. All modern Ford engines are skirted.
Yep.
Steve Rollhick, thank you. Thanks for your time and hard-earned experience. Knife-edged or rounded bullnose counterweights are another option. The directional arrow wing counterweights.
I've went back and forth. I've seen everybody in the industry go back and forth on this very subject. I don't know. I think it's an independent use case. It's a case of how close it is and how close the throws are and whether it works or not in that case. I mean, in one case, you might want a knife edge to throw it off. In another case, you might want a bullnose and make it a wing shape. It just depends on the engine. And nobody's going to spend, 3 weeks on the dyno and 40 grand in crankshafts to find that out.
Ty, I think we kind of went through this. I'll just put it up there. So what can you do for Mopars beside windows on all V8s that are skirted? That's where you get the scrapers and everything else.
You can rip it off the crank and scrape it off before it even gets around the skirt, which is you put sumps down the side right at the center of the counterweight. So instead of a scraper reaching out there, it routes to a sump. Get it off the crank. That's the problem with the full skirted block. It just picks itself back up. So it keeps the oil going around and around.
Now here's one that we kind of talked about. I didn't know this. Pontiac 411. GM had to redesign the LSX block with windows in the mains due to being skirted.
For what purpose? Did they do that for a specific racing class?
Get back to us, Pontiac.
A full skirted block, it's impossible to even control the oil, much less capitalize on or any reduction in windage.
Racer Bob, any different oil control strategies for overhead cam motors?
You're asking the wrong guy. I
There
don't
it is.
deal with them. Yeah, I don't have enough experience to give you an informed opinion on that at all.
Now, Vic Bloomer, he guessed 80 horsepower. He was the highest guesser, by the time you told the answer. Non-skirted wet sump block. What is improvement number one? Good pan?
Again, you see a lot of manufacturers advertising wider pan rails. In the direction of rotation, you will grind the pan rail all the way out to where the oil pan's only sealing on about 1/4 of an inch, right? And then you will relieve that right into the kick out with as big a kick out as you can, and probably a hook trap to carry it around or some other routing. That's the biggest improvement. That's the biggest improvement on a dry sump deal. On a wet sump, you're just putting out fires, doing the best you can.
I'd say it would be a pan,
A good pan and a bad pan is, well, dependent on what engine you're looking at. But a good pan can capitalize on 50% at least of the total friction power available. Wet sump or dry sump, I'm sorry.
Optimum performance. Tim Hilliard. Darin, is it better to separate the sections or have block vents between the cylinder bays? Does this change based on wet and dry sumps?
Well, some people misinterpret the reason for those windows. And sometimes those windows are in there not for venting, but because to prevent a structural stress crack between the cylinders and the main whip, which is a problem on aluminum big block Chevys, certain manufacturers, certain cubic inches. So you'll window that vent. Now, as far as the oiling system is concerned, usually venting is not detrimental. I would say if you did it, it's one of those things where can't hurt, might help, screw it, do it anyway type situations, So, but that also depends on the engine, because the JC51 is not, every single stage is completely different. That way, the transducer could pick up which two cylinders are down or up or different. So I know that the center two is down because the vacuum in that stage is different, yet the pump is, okay, yeah. But in a normal case, venting between there, it's not going to hurt anything, and it might help. It depends on the engine. Let's put it that way. That's the way I look at it. And does it change based on wet or dry? I don't know.
Let's flip a coin. CDB. Tommy, one tip that will get you 6% gain in horsepower.
Go up 10% in cubic inches.
Perfect. Jeff Ott. Yeah. Joel Du Bois, thank you for being here. Hi, guys. Sorry we're late. Don't let it happen again, Joel. We start right on time.
Joel Du Bois, for those who don't know, is the head cylinder guy for Pat Moosey. He does all of those pro mod hits.
Anthony Icavino. Good to see you here, Anthony. Thanks for being here. Great show. Just doing a lot of listening. There's a lot of people that are listening. 143 right now.
143?
He says he couldn't log in. 143, yeah. Couldn't log in. Better to blame the computer than yourself. Eric McMahon. Darin, does your company ever send blocks out or cylinder liners to get them plasma coated? Who can do that?
Who can do that? That's the good question, because we don't do it anymore. We used to, and a lot of people used to. It was just, it caused more problems than the power that it delivered. So everybody got away from it. And I talked with some of the IHRA Pro Stock engine builders and stuff, and them. They were spraying it right on the aluminum, Nicosil right on the aluminum. But it's more of a pain. You can't replace it when the engine blows up. You have to have repairability of those engines. their lifespan, they burn up, they eat themselves up. So you have to have repairability. And a Nicosil liner plasma coating doesn't allow that.
Jeff Ott, thank you, Darin. You're welcome. Turbos welding repair. Do the exhaust crankcase evacuation systems do a good job?
I've spent days and days on the flow bench just tuning that on the headers. And
yeah,
you'll see some of the super stockers will use 2 check valves. And like on the Hemis, you can get 5 to 8 inches real easy. That's easy. Getting anything over that takes an extraordinary amount of effort. And you have to have a converging header.
Yeah.
You have to point that at a certain angle. You have to play with the scallop on the back to try to get the most vacuum you can. Your check valves, sometimes you'll go in there and loosen them up so they'll flap faster and easier. That's about 2/10 of an inch. And then you add another one, and that's a whole inch. Yeah, you're playing the game for all you can get.
Right.
And each inch you get is a lot of power. Because you go from 0 or positive pressure to 10 inches. Well, that's 25 horsepower. So you could scale that from 0, and you go from 5 inches to 7, you just gained a couple horsepower. Easy. And in a super stocker, that's a lot of power, proportionally. So it's worth it. But you're not going to get 10. No, you're not going to get 10. 7, you're going to fight for that.
3 to 5 is what I heard you could get from the bolt-on stuff.
We could get 7, but you're talking about days and days of work.
Ty Hewitt. So you have a 7-quart extra capacity pan and a Mopar. How much oil would you put in it, Darin? 6 quarts? 5?
Loading questions. Depends on the drain back capacity of the top of the engine. Depends on a lot of things. The drain back speed and routing would go into that. And since I don't know that engine, I can't say. But ask yourself a question. Why do you have that 7 extra quart pan?
Cooling.
Why do they make that? It's because it's going to run out of oil because you can't get it back down in the sump. That's why you have to carry that much more oil. So, as you know, the faster you can return it. So, unlike Mopars, we'll actually drill into the back of the block down through the main where we have epoxy filled that for windage, route a 1/2 inch tube on both sides down through that epoxy. So all the oil doesn't go down on the crank, it routes to the back and away from the throw down in the bottom of the oil pan where it can't create more windage and frictional power loss.
You know, Cleveland's have a bad rap for oil control. You know that. But I'll tell you, from the factory, when you look down through the returns on the head going through the block, they are off at least 1/8 of an inch, if not more. I'm telling you, every one of them. You take the time and grind those out to match, go through and where the oil filter bolts on and grind all that out and smooth it out. I mean, those are the little tricks, like you're saying, that make a big difference.
Little mouse ounces, all those little tiny things add up.
Ed's Machine, good to see you, Ed. Hello, Tim and Darin. Thank you.
Hey, man.
Steve Rook says, bay-to-bay breathing for pumping losses versus isolated bays.
Okay.
Not sure what he's...
I don't think there's enough context in that question for me to answer it.
Colin H. David Vizard claims to have measured power gains and effects from these mods.
I'm sure he has.
Yeah.
Every NASCAR team on the planet has isolated friction dynos. They know exactly how much every belt design, how much every pulley design, how much every oil pump design, how much every camshaft bearing takes to turn at whatever given RPM. They have friction dynos. They dyno all this stuff. They can isolate all those factors. I talked at length. I can't say his name. He gave me the dyno data, the data off the friction dyno for 10 different belt designs. There was 2 horsepower between those 10 different belt designs. That's a ton. 2 horse in a belt design? What they did is they went narrower and they went to what they call what is that, a shark tooth or belt?
Yeah, the two. Yeah.
Yeah. They know every single gear ratio, the bypass. See, they have friction dynos because, again, they want to know that pump's efficiency relative to what they have. And they also want to turn that pump only at the RPM enough to feed the engine, sump the engine with as little bypass as possible.
Ryan Morrow, on wet sub non-vac pan, how much is venting the pan worth? Also, for spring oiling, can I just run standpipes in the drains?
Well, yeah, you can run standpipes in the drains. I guess the question is what would be better? And on the wet sump, non-pan vac, okay, how much is venting the pan worth? Venting, in other words, relieving positive crankcase pressure? I need a little more context. But if you have any positive crankcase pressure, that costs you a ton. Just as the first 10 inches will give you 25 horsepower in vacuum or negative crankcase pressure, for every positive amount, it actually adds up more. Okay, why does vacuum negative crankcase pressure create or free up friction power? And people are under the impression that by lowering that crankcase vacuum, it helps with the windage, and it does a lot. You can't create an oil mist with no air. So you have oil falling through and off the crank twice as fast because there's no air. But what people forget is you're not only pumping air in and out of the top, the pistons are moving the air back and forth in the crankcase. So the majority of the power you see is from the friction power you gain from not having to move that air around the crankcase. And it plants the rings.
Right, ring seal.
Yeah, so you have quicker reaction time on your rings, better ring seal. That's another part of it.
Robert Bray, I have a Sonny Bryant NASCAR crank Cleveland. I've had good luck the last 30 years of racing with no rebuilding.
Well, if it's a Bryant crank, that means it's, Bryant equals pretty much bulletproof.
There it is.
You're not going to get a stronger crank.
Jeff Ott, those vents in the LS blocks used to manage pressure between bays because oil drain back was a problem.
Okay. That makes sense. I mean, in a full skirted block, oil drain back is always a problem.
Eric McMahon.
Daily pumps, in my personal opinion, are the best. Period.
There it is.
They take less power to turn. They're more efficient.
CD, B. Nope, you guessed after you already told the answer. Sorry. Now, Ty's getting too much here. Let's see, what do we got? We're going to skip that question for now. Shelton Bars, watching this makes me want to take my short block back apart and make some changes. That's what we're trying to do. Stimulate thinking, make you think about something. And if it means, in the pro stock arena, big deal. You're going to pull that engine 5 or 6 times apart if you had to. It's the little things that make the difference.
Back up here. In direction of rotation on like a pro stock block, what we'll do is we'll grind the pan rails all the way out. The pan rails will go out here and around.
Yeah.
Like that. And we do that so the kick out, the oil can go right off. And like in the JC51 Pro Stock engine that I helped design with Ford, we have the angle at the bottom and the pan rails are wide. So when the oil comes around, man, it shoots right off. There's nothing in the way.
Sheldon, take it back apart. Terry Grover, porting and performance. Tim, don't laugh, but one of my horsepower tricks is just to run 3 quarts of oil and 1 quart of mystery oil, and I've never had a problem with 302s.
Marvel Mist Oil.
Yeah, little red can.
I have no idea. I'll have to ask to a metrologist. What do they call it?
Lake Speed.
Huh?
Yeah, tribologist.
Yeah.
Tribologist.
I'm going to have to ask him what the hell is Marvel Mist Oil, because my old man was freaking so big on that stuff. He put it in every tractor, every lawnmower, everything. And then he put it in his airplane. And the operating oil temperature dropped. So I'm like, whether it made any power or not, I don't know. But it did drop the the running oil temperature. He proved that to me.
I don't know what that is. Have you ever ran 2 different?
More context.
Yep. Hey.
I think you might have
Bill Anderson.
Hey, Bill.
What's up, Darin? Sorry you're late. Don't let it happen again.
Bill Anderson is the one that came up with the Pontiac cylinder head. Just go look his name up.
Yep. You got it, guys. Here he is back. Joel, have you ever tested 2 different oils and systems on the same engine? Example, using the lifter valley as a sump, using oil with more friction reducing properties and separated from the pan.
Yeah. More times than I can count. Have you ever tested 2 different oils and systems on the same engine? Yes. More times than I can count. Example, using the lifter valley as a sump. Yes. Mandatory on any high RPM engine. The sump has to pull the oil out of the top of the engine before it even gets to the crank. Using oil with is more friction reducing properties. Yes. And separated from the pan. I'm not grasping that one. But friction reducing properties. Back 1989, there was a company called Royal Purple. They still make oil today.
Yeah.
And they came to our race shop and they said, try this oil. And my dad said, F you, I'm not putting any oil in my engines that I don't know.
Right.
In 1990, they came back and they said, put it in the engine. We'll pay for it if it burns up. It was a 5-weight oil. Now, you got to remember, back then, everybody was using 1020s. They were using, even 510s weren't even available. And they had a 0.5 weight oil. Well, it was 22 horsepower. But it also went away really quick. So we put that in our competition eliminator engine and ran it and changed the oil every round because the oil would break down so fast. Don't know why, don't care. It's worth 20 horsepower. That's all I care about.
Right.
Changing the oil between rounds was a no-brainer. So we were the first to run Royal Purple oil. And then they started advertising the fact that we gained 20 horsepower, and a lot of other people started picking it up and using it. And it worked for years. I think for a decade, they had just about every pro stock team out there was using Royal Purple oil. And then they they came out with a 0.0, which basically you couldn't even rate the viscosity. It looked like alcohol pouring into the engine. You had to replace it every round too, but it was worth another 4 or 5 horsepower. Of course, all your clearances and everything changed when you did that. You can't utilize the bearing surface areas and clearances and all that stuff and routing and just put a thinner oil in there, your oil flow is going to skyrocket. Well, you're going to have to cut everything back. Well, that's free friction power as well. You're not having to turn the pump as hard to pump a higher viscosity oil through the engine. That's probably half the power we saw.
I'll tell you a story that Warren told me like last week, because I talk to him in the mornings when I'm driving to work. I call him in the morning, bust his ass a little bit, and then we talk about pro stock secrets and stuff. But he told me way back in the day, they always thought he ran special fuel. Okay? And I think I told you this. And they were saying, oh, he's running some additive to it and blah, blah, blah. He said, you know what, Tim? I never ran no additives or nothing. I ran what they gave me. And what I did was I talked with the VP, and I said, I want my stuff in a separate barrel with my name on it. And they said, we can do that, Warren. So he would get his fuel from the VP with his name on it. So pretty soon, people wanted to buy his fuel. So VP said, okay, let's just put his name on it. So they started putting Johnson on the barrels. People were buying them at the races like crazy, thinking that it was some secret fuel. It was nothing special, he said.
See, I won't go into who did it.
Yeah.
But
yep.
I was obviously lied to because the person who had the fuel obviously wanted to try it, R&D it, test it. So by bringing Warren's name up, well, that would get us interested. You know what I mean?
Yeah.
So, yeah.
I mean, he tells me stuff all the time. It's funny to listen to his stories. But the big thing about pro stock racing is not just the engines and the building the engines and the cars and suspension. It's all up here. He said, it's all how you think about it. And when you think about something and put it in a different context, it doesn't mean anything about making your car faster, but you put that idea in someone's brain, and man, they'll go crazy trying to figure it out.
Misinformation was and still is part of the game. At that level of competition, and I saw certain person who shall go nameless.
Yep.
I'm going to protect the innocent. But he was devious because he knew that they were watching and looking.
Yeah.
So he was running a 174 or 172. And by the way, when you're pushing engine speeds up, you don't use a standard rock arm ratio. You use what works. So if you have to use a 1.8235, that's what you're going to do. But he was running a 175 rock arm ratio. He had them stamped 195. That would send any valve train in existence at the time into chaos. And that's exactly what it did. Now, this guy wasn't a pro stock racer. He was a comp racer. And he also built engines. And he had a lot of engines to build after that.
It's all about using your mind.
Monkey see, monkey do will destroy you. You don't want to follow.
Nope. Be the leader, not the follower. Now, I'm not really sure on the context here. Let's see. Pontiac 411. Don't some stock classes such the pan, I think he says suck the near dry on each pass on purpose to free up horsepower?
Yes. Yeah, you're always working on that ragged edge. And if you could, let's say you're in the final round of a race and it's a stalker, okay? Thing ain't going to hit the high side of 7,000 RPM. But if you pull a cord out of there, that's a horsepower. And this guy over here, you're within 500ths. Yeah. You're going to risk the engine to get that higher average power going on the racetrack. That happened all the time. That was normal. And then we had the AccuSump systems.
Yeah.
Are you familiar with that? Yeah. AccuSumps, that fixed a lot of that problem. You didn't have to risk damaging the engine in order to get that oil out of the crankcase. At that point, it made it safe.
I mean, look at Glidden back in the day, in the pro stock days. He used to put molly all over his valve train and not run any oil up top.
Yeah, molybdenum disulfide is an awesome, depending on how it's formulated, is an awesome lubricant. As a matter of fact, it was Mr. Molly, I think they still make Mr. Molly. It's in a small can.
Yeah.
It's molybdenous sulfide
Yeah.
suspended in an oil with a high detergent. So it suspends it. But back in the late 90s, you could take one of those cans and dump it into a Pro Stock sump and gain 2 to 3 horsepower for one run. And then it would all drain to the oil of the pan and you'd have to get it out. So what was funny is you saw guys dumping 2 of those cans in every round. Well, by the end of that race, they had a 1/4 inch of shit in the bottom of the oil pan.
Oh yeah.
But it did make power. It did reduce friction.
The same with rear ends. Drain all the fluid out and put a little of that on the gears.
See, at Burr Morrison, you got to remember, Bruce Allen, our driver, worked for McLaren during the Buick Indy project, and he was part of all that stuff. Well, that's his mindset. He looked at the rear end of our Pro Stock car, and he says, I'm going to build a dry sump rear end, and we're going to see how much it's worth. So he made a sump pan, and he took a battery from a drill and fashioned a pump. So before every round, he would stick a new battery up there, and right before he launched, he'd push the button for the dry sump on the rear end. It was worth $100 or $2 because it pulled all the oil off the ring and pinion and shot the oil right there, and you were able to use a lower viscosity oil shooting right at the ring and pinion because it didn't have to carry it. Yeah, it's worth power. That's those things that you think of that other people aren't going to do or don't know how to do, that gives you those little small mouse ounces that helps you.
Racer Bob, what's the best current coating to reduce wear? Mazda uses nitriding on surfaces like cylinder bore wear on cast iron.
Cost. I think the reason factory uses that is cost. If it wasn't cost, if we were in racing, they would use something a little more exotic. That's easy. So you could do that with standard processes within your assembly line and not have to have new technology, invent new machines, new application, whatever. That's already available. But what's the best current coating to reduce wear? Well, it depends on where the wear is. Valve guides, cylinder walls, bearings, they all take a different approach. The DLC coatings on bearings, I don't see where you could beat that. Chromium nitride, aluminum nitride, there's a lot of coatings. I mean, you'd use a chromium nitride on a valve head, something that's not going to really wear, but the only reason you use chromium nitride on a titanium valve is because titanium is incompatible with any other metal. So you have to have a comparable difference in hardness and softness to get a comparable wearability. In other words, 2 surfaces that are hard and hard aren't going to wear. But if you have a hard and a certain degree of soft, the soft is going to give to the hard, form a surface, and the hydrodynamic wedge of the oil will jack up and go over that, and it won't break down as easy. But titanium is incompatible with any other metal. So whatever metal it touches, it galls to, period. So you need a harder metal, which is chromium nitride. You're not going to get any harder than that. And yeah, it might be microns thin, but that's all you need. But you wouldn't chromium nitride anything else. You would use a different approach. So every friction reducing coating has its place within the engine. And friction coatings are worth power. They definitely are. Thermal barrier coatings, however, I don't even mess with them. Don't want to mess with them. Mess with them, no more. Here's why. If you have a piston that's designed to operate at a certain thermal coefficient across its face, its head, And that thermal realm equates to so much expansion and contraction. That's what that piston is designed to do. And then you put a thermal coating on the top, you change all that. Well, you could throw that piston, you could throw the rings at a seal, you could do in a high RPM engine that's on the edge. Yeah, just no. But friction coatings, yeah, anywhere you can use them.
Jeff Ott, I heard Warren Johnson would measure temperature of belts for friction. Yeah.
That's cool.
He told me that.
I never thought of that. That's so simple. Shit.
And listen, after this, I'll tell you something that will blow your mind. I can't talk about it on live because he told me he won't tell me.
I love feeling stupid.
Yeah. Yep. Thanks, Jeff. We appreciate that.
You could literally have a thermometer or thermal probe aimed at that thing and watch the temperature vary. Okay, go ahead.
Right. Then you can change the belt, right? The width of the belt, the pulley, whatever you want to change.
In ProMod belts, of course, when you're making that much power, the amount of friction power that belt takes is secondary to it just living. And we had belts early on where we went from a 1/2 inch to a 3/4 diameter exhaust push rod, because it's hard to open the exhaust when the push rod's this freaking long.
Yeah.
So a 3/4 diameter exhaust push rod would open it immediately. Well, that put a lot more strain on the belt. The belt literally at higher RPM down track couldn't open it and would skip a tooth or two. So the engine would come back and it'd be 20 degrees retarded in the exhaust through. Yeah. I'm going to take a short break. Then we'll come back.
Yeah. Don Dotter, I remember Warren Johnson. Listen, that guy I'm telling you, he is a worker. He busts my ass about work, and I work 12 hours days. That guy works 7 days a week, except for Sunday. He only works usually somewhere around 7 or 8. He's done by 4 o'clock. But otherwise, he's at his shop working at, I try to catch him off guard. I've called him at 6 o'clock in the morning. He's like, oh, what are you sleeping in? So that guy's a worker. He said, you got plenty of time to sleep when you're dead. And my dad said the same thing. So I like that. And Don says here, I remember Warren Johnson measuring the temperature of belts. The stuff that he did, it just blows me away when he tells me the stories. Improves ring seal. So I think they might be talking about the vacuum pump, which is what we had talked about. I care about my sump. There you go. You know, if you're going to invest in an oil pump system, you know, versus wet, dry sump is the way to go. So he and I are building a Pro Stock Cleveland. The heads are sitting back there on the bench. He's working on the block now. And I want to make a wet sump, and he just told me he doesn't want to do a wet sump. So it's going to be a dry sump Cleveland like the Pro Stocks were. And our goal is going to be about 850 horsepower. And he said, is that all you want to make? And I said, well, I think
Glidden, back in the day, he used the shotgun method. So he tried anything and everything and worked around the clock. And his kind of motto was, I have to keep my lights on 1 to 2 hours longer after the other guy shuts his off.
And Warren told me he is more of a scientific method. He will do things in a scientific method, this way, this way, this way, and this way, and that's how it works. He doesn't change.
You can't use the shotgun method anymore. It doesn't work. Either you design it to do what it needs to do, or it's not going to do it.
Ed's Machine. Hello, Dean. It's good to see you here. He's talking about Dean Stevenson. Now he's from Australia. Junkie, DBGU, and DMI are #1. Thanks, guys. Hey, we appreciate it. You know, we got 150 people here. Someone mentioned, well, Uncle Tony has a live tonight too, and I'd rather be here. It really comes down to what you want to learn. You know, we're talking here cutting edge versus some
Uncle
stuff
Tony.
that
Uncle Tony.
He's a YouTuber he's more Mopar related. In fact, I had him on for a live chat when I first started. You know, he's just old school. He used to do some Top Fuel crew work. So he knows some of the old school type stuff. and likes to talk about it. And he's got some great stories and does some good stuff. It's just that, you know, there's different levels, and we're just at a different. We do things differently here at DragBoss Garage.
The thing is Top Fuel is a completely different
than Pro Stock. Yeah.
Yeah, and to think that I can't learn something from him, or he can't learn something from me is, well, that's silly.
Can't be that way.
Of course we can. Yeah, he sees different loads, characteristics, he sees a lot of different things that I might not see that give me insight into something I may see. And I have never tried to sequester myself away from other cylinder head guys and engine guys. I've always tried to collaborate. And now it's about 2010, 15, it's just exploded. Everybody started to really collaborate with each other because stuff started getting more expensive and a lot harder to do.
The more you know, the more you know. That's how I look at it.
The more you know, the faster you go.
There it is. I got to remember that one. Hey, I like that, Darin. CDB. This is a tough question, I think, to answer. But how much horsepower does the cam through the whole valve train equal, say, NASCAR versus Pro Stock versus Pro Mod?
So you're asking what is the total friction power of the valve train itself?
Yeah.
I hope. Yeah. Ooh. I've never quantified that myself. I've never been on a friction dyno in order to do that. So I can't tell you. But I guarantee you a NASCAR team will tell you exactly how much power their valve train takes to turn.
Oh, yeah, without a doubt.
And, you know, it's money. If there's enough money and enough sponsorship for the equipment and the data acquisition time, yeah, we'll do it. And NASCAR is, you know, it's like up until 1995 or 6, the drag racers fed the NASCAR guys power. And then all of a sudden, they started taking off. Their engine combinations are quite different.
Right.
So their engineering started specializing in that combination. And they're the ones that came up with valve loft because the flat tappet cams were so limiting. They learned how to loft that valve. Well, all that technology came into Pro Stock, and boom, we went from 9,200 to 10,500 in less than 5 years.
Bill Anderson donated $1.99. Thank you, Bill. We appreciate that. Turbos Welding and Repair. Uncle Tony's Garage should be watching this live on his live. He's welcome. Come on in, Uncle Tony.
You can always watch it later.
That's it. That's why we put on the replay. It's there when you need it. I mean, we're at right now. We said before we start, let's do a couple hours and no more of that 3-hour marathon. We're already at 2 hours and 8 minutes, and it's like there's still a bunch of questions to go through. So we kind of gave up on worrying about the time limit now. When we're done, we're done. You know, not that we're going to be here for 4 hours. Let me tell you that. My ass won't last that long. Ty Hewitt made a new friend today. Ron Browning came by the house. Stock Eliminator. I bet he would enjoy this conversation. There it is. He's welcome to watch it on replay. It's there for him.
I've always said that if you want to learn how to build engines and extract power, stock and super stock engines are an excellent training ground because the restrictions are many and the ability to extract power from those combinations is extremely limited. So it forces you to think. And it from a super stocker to a pro stocker, you're doing the same things: friction reduction, oil routing, all that stuff.
Bill Anderson, let's talk about main and rod bearing diameters being reduced in size versus coefficient of drag values.
I could never tell you exactly what the change in coefficient of drag is. It's kind of like that ABA testing. If you test, if you don't know the formulas, the math, or anything else, and you test something, and then you test something else, and you see more power, and you go back and you see less power, and you go back and you see more power. Okay, that's the right direction. no matter what it is. Okay. So that's basically the approach we always took to main and rod bearings. Was, of course, when you reduce the diameter, you reduce the bearing bearing surface speed. And that alone is a reduction in friction power.
Sure.
So if you took like a 455 Olds with like a 3125 or whatever main, a huge main, or a Pontiac, it's 3-inch diameter main, and tried to turn it up, the bearing surface speeds can get out of hand. They used to get out of hand really bad, but now we have better oils and higher shear strengths, and you can wind them up a lot more. But you would never want that much bearing surface area and surface speed in a high RPM engine. You want to reduce that down. So you reduce the diameter down to reduce the speed, and the width to reduce the unit loading area and friction. So if you look at a Pro Stock, we went down to even a Corvair rod, which is a 1770, but a 1880 is pretty much normal. And a 427 main is pretty much normal. You go down as much as you can, and if you shrink the main too much and you don't have enough overlap on the crank, or that rod pin is too far away, that can cause all sorts of other issues. So you have to take everything into account, not just the frictional power reducing that, because it changes crankshaft weight, placement, diameter, everything.
Koala Squad. Can adding an oil accumulator to a wet sump system help with crankcase pressure and allow more vacuum from the vacuum pump?
Okay, an oil accumulator. You're going to have to define what you mean by accumulator.
Like the
wet sump.
That's what I thought he was talking about. AccuSump that stores like a quart of oil.
Oh, no. Mm-mm. An AccuSump is just there to get oil out of the pan of a wet sump. The dry sump does that automatically by distributing it in the sump. So you don't have to try to get oil out of the crankcase. In a wet sump system, you have to carry more oil than you actually need to make up for whatever the lack of drain back is. So if you're down track 3/4 of the way and all the oil's in the top of the engine, you're going to starve the sump. So you have to run more oil than would otherwise be necessary. Well, that oil creates drag. So if you can get that oil out, and by 3/4 half track, the sump goes dry and you can feed it back in, that's less oil the crank had to pick up and carry with it. So it's free power.
Yeah, they have timed. They have timed release on some of those AccuSumps where you have a solenoid in there that opens up at a certain time in the run for that.
Like or it just senses a drop in pressure and reacts instantly.
Thanks, guys. Appreciate it. Matt Hummel, can you starve a flat tappet cam by controlling windage oil too much?
Yeah, absolutely. Absolutely. I mean, a flat tappet cam, it needs oil flow because you got to, one, carry the heat away, and two, you got to have a certain amount of lubricity there. Otherwise, you're going to chew them up. Flat tappet cams are not something I've messed with almost at all because it's like, in my personal opinion, unless the rules dictate it, you're not going to use a flat tappet cam. A racing engine doesn't have a flat tappet cam because it's so limiting.
The Nova Man.
I don't know if most people know, but I mean, the extent of engineering and the money that went into making a flat tappet live in NASCAR is insane. I mean, Stellite inlaid cams and the money they spent trying to make those things live, they could have converted to a roller and been done with it. But oh well, that's what they wanted.
Where did the mushroom tappet cam come into play in regards to the flat tappet cam? Do you know what I'm talking about?
Well, the NASCAR wanted to run bigger lobes, and the amount of lift you can run is proportional to the diameter of the lifter of a flat tappet cam.
Okay.
A roller cam doesn't see that. So if you have too big a cam and you have a lifter this big, it's going to come around and slap the side. So you have to grow the diameter so it hits. So
perfect.
The mushroom lifter was a way to make it wider and keep the same bore.
Okay.
Again, flat tappet cams are a pain in the ass because they're really not meant for racing at all.
Go roller.
And it's one of those things where all these rules that come in, you got to use a flat tappet cam, you got to use a cast manifold, you got to all that stuff really was instituted because they wanted to keep the cost of racing down. But they spent $100 million trying to make a flat tappet cam live. That didn't save any money at all.
I can tell you my own experience. I ran a flat tappet cam and was running 1205. I put a solid roller in it, 1125 right off the trailer. The Nova Man. How would a shade tree drag racer go about determining the optimal oil level? Run enough so you still have oil pressure at the end of the run.
And it's a good question because it depends on the engine, the oil pan, and everything. So how do you determine that? Well, you're not going to see it on the dyno because it's dynamic on the racetrack.
Right.
So on the racetrack, the G-forces send the oil back. So the oil routing will be different than what you would think a lot of times. And two, watch your oil pressure gauge. If she's dipping and bobbing at the 1,000-foot mark, well, you might want to add a quart. And if you add a quart and it stops that, well, you know she's running out of oil. Oil pressure, run enough oil pressure so you run enough oil so you still have oil pressure at the end of the run. And see, you've hit on the inefficiencies of a wet sump system. You have to run more oil than would otherwise be necessary because the drain back and the routing, you can't get it back down to the sump. So yeah, how do you quantify that? You watch the oil pressure gauge. And every super stock racer in the world has made a run, drained a half a quart, made a run, drained a half a quart, made a run, drained a half a quart, and watched it until she bobbled and add a half a quart. That's where she wants to be.
That's shade tree right there. Turbos welding repair. Smokey tried polyester airplane oil back in the day.
Yeah, we even tried turbine engine oil. We tried everything. Everything. The oil wars were before the fuel wars. The oil wars started in 90 and ended probably about 2000. And the fuel wars started in 90 and ended about 97 when they had us fuel rule and NHRA. I mean, the fuel rule killed people. I mean, we were mixing some nasty, nasty toxic shit. I mean, propylene oxides, dioxanes. I mean, when I was a kid, I was 22 years old and I was mixing fuel.
Well, didn't you tell the story where you were putting some additive in the dyno and David Rear came in and said, "What the hell is that smell or something?" He said, "We're not running that."
That was the ELF catalytic fuel. That was the height of the fuel wars. That was when everybody was looking for any power possible, and there was a lot of power in fuel. Because the racing fuels that we had reached a point in engine speed where we needed more burn rate. So faster burn, lighter ends, lighter fuel, easier to evaporate. And we needed it bad. So any gain at that point in that area would pay big dividends at power, where now it wouldn't. You would have to redesign a lot of stuff to even make it function. Right. Back then, it was just power in your hand. So, the C44 fuel came out, and I've told this story a lot of times. We were qualified, I think, 6th at Dallas. And David did not want to run the fuel because the rule book didn't specifically state it. C44, he went up to Graham Light and he said, "Here, sign this paper, say it's legal." And he did. We put it in the car and went, boom, number one. Qualified number one 6 or 7 times that year and won 4 races. That's because C44 was worth $40 horsepower. And everybody else had it a year or two before we did. You're not going to redesign that engine and raise the engine speed and make 40 more horsepower. You're not going to get around that. If they have a fuel that's worth 40 horsepower, just like today, if somebody else had a fuel that was worth 40 horsepower, you're not going to find that in the engine itself. So it's good that they have a fuel rule. Excellent. That needed to happen. Now the ELF catalytic fuel was worth another 20, but it was also toxic. So
you're right. When you're running for championships, deception is totally illegal. My opinion. Okay, you're right.
It is.
Mm-hmm. Brian Cool, what's up, Brian? Good to see you here. How much material can you take off the main caps on a Cleveland and still render it safe? Thank you for the content.
Depends on how much power you're making.
Yeah. They're strong
if
caps.
If you're making 600, you could whittle them down to almost nothing. If you're making 1,500, probably just don't touch them.
Jeff Ott, less oil helps raise its temp too. So that is a win for drag racing. I don't know if do you believe that? Hotter the oil?
Okay. Okay, it took me a minute.
Yeah.
What he's alluding to is hot oil is thinner and will make more power. You see that on the dyno all the time. That's a given. Just so long as the block temperature maintains the same and head temperature. If they all go up in temperature, it's not worth that much. So, a long time ago, with the thicker oils, we would have pan heaters. We would heat the oil, almost boil it.
Sure.
I mean, get it as hot as we possibly can until it almost started to break down before we made a run, and try to keep the engine and the heads as cool as possible. But nowadays, we have oils with a film strength 10 times higher and a viscosity 30, 40 points lower that flows just like that better than that hot oil ever could. So we can ice down the whole engine down as low as it'll go. So, and I often tell the story of the Spirit of Rhett, the car that went 422 miles an hour, and we did everything everybody said wouldn't work, which was nitrous and carburetors and gasoline. And what a lot of people don't know is that thing hauled 45 gallons of ice water, and the oil was zero weight. So that engine never got over about 120 degrees. It made 20 runs. It looked fine. So in the old days, what you would have to do is heat the oil up and make a little more power, but that also heats the block and the head. So an engine's power is directly proportional to a difference in temperature. Look up the Carnot engine. Look up energy. Difference in temperature is relative to the amount of power extracted.
Bill Anderson, 199. Thank you very much. Appreciate that, Bill. Eric McMahon, Darin, did you ever mess around with reverse rotation engines for circle track?
No, never touched one. I've seen a lot of them in boats, but I've never even worked on them.
Now this one's way off topic, okay, Pontiac 411, but we're going to put it up there for you. Darin, did you ever complete the home subwoofer amp?
Yeah, albeit really badly. Yeah.
Okay.
I messed around with that thing for about 2 months. Just fine-tuning it, you know. I'm not an electrical engineer. I play. That's all I do. As far as designing electrical circuits, I'm a babe in the woods, you know.
Well, you keep working at it, Morgan, and I think you'll do all right someday.
I don't have my 10,000 hours in yet.
I saw that.
They've done a lot of research. It's about 10,000 hours. If you want to be proficient at something, you have to give up everything in your life, concentrate 10,000 hours, and you'll be pretty good at it.
It's just like being a PA. If you go into any specialty, I don't care if it's emergency medicine, cardiology, cardiac surgery, you ain't going to know nothing until at least 4 years in, maybe 5 years. I mean, you'll know what's going on in 2 and 3 years, but to be proficient and to be able to work on your own, it takes 5 years, man.
At least. And that's what I tell people that come and want me to train them to port heads. 5 years to get your legs, just to understand, get a feel, develop your technique. 5 years. In 10 years, you'll be able to rock and roll, go out on your own. But it takes a decade to learn anything.
Oh, yeah. Well, we kind of talked about this. Darin, do you think hard anodizing pistons and grooves is a good thing?
It has its place. Is it a good thing? No. No. In almost any other way other than the fact that in extreme heat and power conditions, when you're making 3,000 plus horsepower nitrous or supercharged and want some higher level of endurance, anodizing pistons can, in certain instances, get you there, but it also knocks the crosshatch out of the cylinder walls, and if it ever comes off the piston, it takes the rings out. Yeah, it has its place. I've never used it because I've seen it used in certain engine combinations, usually supercharged stuff that its heat is way out of what the engine can take out and cool, but it has its place. It can band-aid a problem where you're melting pistons, but it's not going to cure a bad tune-up. If the engine has a bad tune-up and it melts or melts through a piston at a certain point, all anodizing will do to you is delay that a couple of milliseconds.
All right, Pro Mod Racer. I'm on the floor laughing at how excited Darin was on belt temps.
When I learn anything new, I get excited.
That's it. I hear you.
Because I'm sitting here going, why didn't I think of that? God damn, this was simple. Jesus, I'm an idiot.
All right, Bill's got another question. Talk about micro polishing of the crank in terms of oil windage. It's good.
Yeah, I mean, the parkerizing, the micro polishing, oil shed coatings. There is a specific polishing technique and coating where if a crankshaft's on the floor and you have oil in your hands, I dare you to pick it up. You can't do it. You literally can't do it. If you try to pick it up by the throws, you can't do it. That's how slick it is. It's ridiculous. Well, the difference between a micro-polished crank and that crank might be 1/10 of a horsepower, but that's another 1/10 of a horsepower.
I like this one here. Tim, I've never seen a more impressive finish treatment on your 408 crank. Yeah, that was done by a guy that used to work at Callie's. He left Callie's and has his own, damn, what is the name? It escapes me.
Yeah, what? I know you're talking about.
It's like, I can't think of his name now because I thought about it too quick. But anyways, I'm telling you, it looks like chrome. It's a, and I can't think of the name either. I'm sorry, guys. I'll put it on in the comments or something. But it's a finish that's like unbelievable. Talk about shedding oil. Nothing wants to stick on that. It's mirror polished. So yeah, the guy used to work for Callie's. He left Callie's and started his own. It's in Fostoria, Ohio. I'll think of it in a little bit. So. Can Darin explain coefficient of discharge and explain the numeric values? George, good to hear and see you.
Any coefficient, a coefficient is a number that serves as a representative of other variables in an equation. Basically, what you're trying to do is you're trying to quantify, by whatever means you derive this coefficient, what is the maximum potential or 100% of what I'm working on. So, and there are a lot of different coefficients to use. The discharge coefficient that I use, and a lot of people use in the industry, is a flow bench coefficient, which is on the flow bench at 350 feet per second, 28 inches, you're flowing 146 CFM per square inch of valve area through that orifice. So that's your 100%. So that port's flow and any area in that port is related, proportional to that. That's your coefficient. So if you're flowing 120 CFM per square inch through your push rod, it's 120 divided by 146. That's your coefficient. That's your percentage of 100%. How efficient are you? So when you're flowing 136, 138 CFM per square inch of valve area at the throat on like a Pro Stock or Comp or Unlimited NA engine, that's 92% efficient on that discharge coefficient. But there are 5. Depends on which one you use. Again, most people use the flow bench because we can talk to each other. But you also have an open port flow coefficient, meaning the valve out of the port at 28 inches, how much does that flow? And every area in the induction system is related to that, okay? Or you have an open pipe coefficient of a certain diameter. That's too complex. Then you have the Hemi flow coefficient. Well, a Hemi has the highest flow per unit area of any cylinder head in the world, so you use that as your 100%, and your coefficient is related to that. So that's the easiest way I can explain coefficient of discharge in a port and the way we do it. There are other ways to do it, much more complex ways. We don't need to do it that way.
So the place is called Shaft Tech. I put it in the comments, and it's called Omnicron. That's the finish. So if you guys are interested in that. James Miller, the Spintron has a 50 horsepower electric motor to spin the valve train. I was surprised how loud the valve train was on a Spintron.
When you're standing at the big end, and you hear a Pro Stock engine go through the gears, and you hear that whine, that's 80% of the sound you're hearing is valve train noise, not the exhaust. The exhaust is pointed back the other direction. You're hearing the engine scream is what you're hearing. Yeah, they're loud.
Ken Moole, the trickle-down effect is definitely tied to knowledge. More is more. There you go. Mike G says, big money was dumped into NASCAR in the middle 90s, hence the development and advances. You know, like Darin always says, the valve train is what brought these Pro Stocks alive, being able to handle those high RPMs. Mike Cranston, it's good to see you. I haven't heard from you in a long time. Mike, hello, Tim and Darin from New Zealand. Great work. Followed Darin for years, and his knowledge has never let me down. There it is. Thank you.
You're welcome.
Jeff Ott, valve train is unsettlingly loud. I have torn back in my own motors on the stand after hearing what sounds like rotating it.
I can't. Anybody who goes to see a Spintron test for the first time is shocked to their core because it's 100 decibels. It's loud. Really? Yeah.
You know, the AC brings up a good point. Has everybody hit the thumbs up or up button? Here's what I'm going to tell you. I even talked to Darin about this a while back. You know, I see a lot of these guys when they make a video, at the end of it, they're always saying, please like and subscribe, you know, donate and do all this stuff. I gave up on that stuff a lot. I do appreciate the likes, no doubt. But I said to myself, I'm not going to beg for subscribers. I'm not doing that. You want to subscribe to our channel, you're welcome to it. If you don't. But to sit there and every video they say that. Now, some of my videos have it written there, but I don't talk about it.
That's kind of funny you say that because I've always found that somewhat unnerving when they do that.
Well, you're begging. I never was a beggar. I never will be a beggar. I'll go hungry before I beg, you know, and I don't think that's right. We do this because we want to entertain you or we want to teach you something. That's why we're doing this. We're not doing it to try to get more subscribers. That'll come when it comes. I don't go for that. Just like people said on here, well, how come no one's donating money? You guys know how to donate money if you want to. We're not going to ask you for that. You know, would it make us happy, or does it help give that money to Darin? Sure. But we don't care about that. We're here to have fun and learn what we can. That's not our goal. So thanks for bringing that up, AC.
In this game, if money is your objective in any way, shape, or form, I got news for you. You're in the wrong game.
Yeah. You know, we've already been going now.
You don't make a lot of money in this game.
A lot of time. You spend a lot of time in this game, I can tell you. You're making videos. You already know. The last video you put up, you texted me messaged me a couple times. Look, I got to change this. Look, I got to do this. You know, it isn't like you do it and you make that video in 1 hour and it's all good to go. I mean, you spend days on it, hours on it.
I spent 2 days on this.
On this presentation. Yeah, two full days. You know, 12-hour days, not, 3 hours here and there. And
I'm going to Rottler in Washington to give a presentation, here in 2 weeks. Okay. And I've been working on that one for 3 or 4 days.
Greg Ertman, the bearing speed reduction is part of the whole point of a clamshell camshaft. That and the size of the cam. Now, Warren Johnson told me he had been doing a clamshell camshaft. I thought he told me 30 years ago he did it.
The technology for a lot of the stuff that you see out in the aftermarket and generally available has been around for decades.
Yeah.
It's just getting the machining processes and making it profitable. I mean, okay, how many clamshell are you going to sell? How many of those are you going to sell 1,000 when you could do something else and sell 10,000? Well, it does all come down to money. It's like, why do you see nobody designing new intake manifolds? It's because you only make $100 a piece and it costs 60 grand to make a core.
Yeah.
So everybody just goes, screw it. We're going to make a 3D manifold and it's going to cost us $4,500, but I don't have to drop 60 grand in tooling to make a set casting that never changes. 3D, I could change it whenever I want.
Mm-hmm. Thanks, Greg. Optimum performance. Tim Hilliard. Valve train loss goes down with RPM. Rotating assembly goes up with RPM. This is relative to all frictional losses. As one uses more, one may use the same, but will show it using less.
Valve train loss. Yeah, I think you're going to have to contextualize that a little more. Explain what you mean by valve train loss goes down. What exactly is the loss that goes down?
Durability.
Oh, well, yeah. Absolutely, durability does, but power goes down.
Down too. Rotating assembly goes up with RPM. Makes sense, right? It's going to spin faster the faster it goes.
The frictional power goes up relative to engine speed no matter what it is.
As one uses more.
If it's turning and you turn it faster, the frictional power loss goes up proportionally.
Goes up, yeah. As one uses more, one may use the same, but will show it's using less.
You're going to have to explain that one.
Yeah, I'm lost on that one.
It's hard to formulate probably what he's talking about in that short a sentence. That's the problem. Sometimes asking questions like this is you're trying to boil a complex question or answer down into 2 or 3 sentences. And, that's hard to do.
Well, you could do a whole video on it. Terry Grover, porting and performance. Darin, I remember guys talking about the 460 Ford saying that the big bearing helps the engine live as long as you don't turn it over 7,000 RPM. What do you think?
The big bearing and the bearing diameter and the rod diameter and its intersect makes the crank stronger. But you're never going to reach the point on a stock 460 where the strength of that crank becomes an issue relative to the bearing speeds will become an issue far sooner. Let's put it that way. But yes, that is true. The bigger bearing is stronger. It is more stable. Absolutely. And he is right. If you turn it over 7,000, you got to make some changes. You got to increase the clearance. You got to do certain things because the bearing speed gets out of hand. Pontiacs, big block Fords, Ols, yeah, all of them.
Now, here's another thing that I think of when you ask that question, Terry. Remember, the 460 has the same oiling system as a Cleveland. Okay, if I'm not mistaken, am I right? Non-priority. The issue is with a Cleveland, once you go past 6,800, that's when you start to see the oiling problems with a Cleveland. You can run them 7,000 and below, you won't have any issues with oiling. It's once you start to go past that magic number of 7,000. So that could be contributory also. That's how I kind of look at it.
Any OEM block used for racing, you have to make changes to the oil galleys, crossovers, rerouting, restriction, what have you, because they were never meant to do what we're trying to do with them. I mean, a race engine, like the JC51, those oil galleys, everything, it starts out big and it gets smaller as it goes. So the velocity maintains the same. I mean, things that nobody thinks about are incorporated into race blocks to maintain a steady oil pressure and flow rate, more importantly. Yeah, any stock oiling system, the higher you wind it, the more difficult it gets to manage. I like telling the story. You never know what's going to bite you. Everybody has heard of a cross-drilled crank, right?
Yeah.
Okay. Have you ever heard of a butterfly drilled crank?
No.
Back in the Can-Am series, the 302 Fords, they had, I think it was like 27 or 37 crankshafts made that, and I haven't seen one for at least 3 decades, but I used to see them floating around all the time. And what it was with the main, instead of being cross-drilled, it was butterfly drilled, so it intersected in the center. And the rod was drilled to the center of that hole. So now you have an X pattern with the rod feeding from the center of that main. So as soon as the rotational engine, the engine speed got to a certain point, the centrifugal force would overcome the oil pressure, throw the oil to the outside, starve the rod, and boom, out the side. And that RPM was 8,800 on the nose. No matter what oil pressure, it didn't matter. The oil system was restrictive enough to where it doesn't matter how much you increase the oil pressure, that 8,800, the rods were coming out the side because it just instantly starved them. That was a case I have seen twice in my entire life and haven't seen yet. But it was just one of those weird instances where we blew up 2 engines because these cranks were done in a way we never imagined.
Yeah. Bill Fioretti. Hi, guys. Just returned from a large family outing and a long drive back. Old guy. Long day, long drive. Just hopped on to say hello. Hello to you, Bill. We appreciate you being here. And yeah, that's what we said. We said that before about the replay, guys. Many guys come back and watch this, or if the word gets around on Tube, next thing you know, people start watching this. So thank you, Bill. We appreciate it. Roland Tabacchio. The guy asked about titanium main caps. No. Used by the Motown missile. Did absolutely nothing but take 7 pounds off the front of the car. So that's from back in the day with Don Carlton.
And that was...
Thanks, Roland.
Yeah, that was something you could do. And then you look at that today, if we made titanium main caps, they have a higher modulus elasticity, meaning the rubber bands. So at the power level we are now, that won't work at all because you're going to have cap walk like crazy.
Bill Anderson, flat tappet cams are yesterday's news. There you go. Not for racing engines. Thanks, Bill. We appreciate that. And this is a popular mod, NASCAR guys. It says, let's talk about oil sprinklers and the valve covers and piston squirters. So NASCAR had a lot of the valve train, the oilers, spring oilers. Piston squirters, I know today's engines did. I don't know when that came around, but a lot of the foreign engines had piston squirters way back. Can't tell you the years or what makes, but I have seen that in the past. So appreciate that, Bill.
Well, I was going to go to my computer and grab some pictures of the worst catwalk I've ever had, but I'll save that for later.
Okay. What do you think, Darin, about oil, like spring oilers and the valve covers and then piston oil squirters?
For endurance applications, I feel it's mandatory.
Any NASCAR, any endurance.
Those spring coils generate a ton of heat. And especially on the exhaust side, you're sitting over the exhaust port that's hot anyway. Yeah, you need to cool those springs down. And that's what oil does. It's like there's a new aircraft engine. People forget the fact that the oil carries a ton of heat away from the engine. And there's a new aircraft engine, and I forget where they did it. I think it was South Africa or Czechoslovakia, but they designed this engine. It's smaller displacement, higher revving, reduction, and it has 2 huge oil coolers on it. And it's a water-cooled engine, not air-cooled. This engine is set up to where if it loses all its water, it can reduce itself to 50% power and cool itself on the oil coolers alone. That's a hell of a safety factor.
Yeah. Amazing technology. Joel Du Bois. Many times adding oil to the sump can increase oil pressure loss from the oil wrapping around the crank.
Yeah.
And pulling oil out of the sump. Look both ways when you see oil pressure loss. It depends.
Good point. I'm glad you brought that up. Yeah. I mean, the viscosity of the oil, if you fill it up too much, that crank throw will come up and grab it and then the power will go. And then it will literally starve the sump because it's all up in the crank. And a full skirted block makes that twice as bad. 10 times as bad, actually. Thanks for bringing that up, Joel.
Breton Marusik. 25 years, we messed with flat tappets. Finally, the rule changed last year. Not a minute too soon. Joel says
every time any sanctioning body instigates a rule to keep costs down, people will spend 10 times the money getting around it.
This is good too, Breton. Hey, Joel, I'd like to just know what you've forgotten, which brings up a good point. And this is exactly why we're doing this. And Darin and I were talking about this before the live chat started, that this is it. You know, this is the documentation that his life's work, this 40 years. And this is what these presentations are. And this is why we have this channel, to record history, whether it's Darin's or anybody else that's in the know. Joel, maybe we can get you on here too, so that guys can see this in the future when we're dead and gone. Because I mean, our lifespan, our lives are already, they're half over, Darin. Probably really 3/4 over if you want to look at the number.
Shit, I'm 75% done, man.
All right, I'm 75 too. We're the same age. Let's see. Yeah, you too. I told my 15-year-old the 10,000 hour thing. He said he almost an expert at video games. There you go.
I added it up. When I learned about the 10,000 hour rule, I was like, how many hours do I have? And I started adding up, and I was like, no, that can't be. And then I thought, okay, well, the trick is it takes 10,000 hours in a specific discipline to become a professional. So that would mean cylinder head machine work, cylinder head porting, manifold design. So you'd have to have 10,000 in each individual discipline to be an absolute expert in all of them. So head porting, cylinder head design, intake manifold design, yeah. Okay, I've got plenty of hours there. Engine building, engine design, no. That's why I say I'm not an engine builder. I specialize in this area. And so I added them all up. It was 75,000 hours.
Wow.
That's what I have in the cylinder head game as far as and fabricating manifolds and cylinder heads.
I got to figure that out. 75,000 hours.
Yeah, I mean, since I was 19, I'm 60. So if there's 200 work hours,
That's
just say
36
200
years.
days. Huh?
That's a
Yeah, that's
normal
36.
week.
I'm being conservative.
Yeah.
If I said 80,000, nobody would frickin' believe me.
Let's see. Now this is interesting. I mean, I know this has been around. Mike G, any testing with cold fuel, dry ice dropped in the fuel cell, etc.?
Decades ago, back in the 70s, 80s, the fuel that we were using responded to being cooled down. And I'm not a petrochemist. I can't tell you exactly why. Modern fuels, that's not the case.
I mean, think about the old days.
I haven't seen it. Still try it. Even heating the fuel. Tried that too.
Do they still even use cool cans anymore?
Mm-mm.
I mean, I haven't seen
the
one.
Light ends of the fuel, the ability for this fuel to phase change is so fast and so easy. It's not like the old fuels that were really hard to atomize. And the fuel density itself, what they were doing is increasing the fuel density relative to what was coming out of the jet. So that it doesn't translate today, let's put it that way. And I really can't elaborate on it.
Pontiac 411. Could there be any benefit to running a head gasket with no cooling passages and cooling the heads and blocks separate to keep the heads cooler?
Do it every day.
It's like dry deck, isn't it?
Yeah, do it every day. Solid block, water through the heads. And in those cases, even with thinner oils, you can put a little bit of temperature in the oil. And the cylinder heads will be 50 degrees. And by the time you turn the engine, hit the ignition, it'll be maybe 100.
Ty Hewitt, Rain-X for oil. You know what, Ty? Tell your buddy that has a super stock Hemi to put Rain-X in it and then test that and then get back to us on that. I think that'd be a great experiment. Hey, Tim, what's the name of the carbide shop Darin said the other night? CFS.
SFS.
SFS.
SFS carbide.
And I put that in the video that we made. I put it in letters because when he said it, I was like, what the hell did he say? Then I looked it up. Had to ask him again because I just couldn't hear it. Eric McMahon, how long until Spinal Tap 2.0 ends up in a car?
I don't know. Any project like that takes years. I mean, just the testing and R&D, the Spintron, the new valve train we completely made from scratch. The heads we completely re-engineered to fit onto it. That took 1.5 years. The Spintron testing's another 6 to 8 months. It takes years to do that stuff, to hit that mark. So it'll probably, after the engine's done, you might see it in a car 2 to 5 years after. Who knows? Or maybe a year. I take on what I call 3 special projects a year, whether that be the super stock Hemi. Well, special projects are projects that I know I'm going to have to put 200 hours in.
Mm-hmm.
So I have to kind of allot that time. So I've got 3. So that would be like the Pro Stock Hemi and the JC51 for Clinton F or something like that.
Thanks, Bill, again. Here's another question. Talk about IPNing of the crankshafts, ion plasma nitriding.
I don't know enough about it to give you an educated opinion. I would just be talking out the side of my mouth.
Thanks, AC. It does help the algorithm. And I see that when I look at the stats. You know, I always look at the stats on how my channel's doing that because that tells me where we are. Are we doing what people want to see and what they want to hear? So, yeah, thanks for the thumbs up and the likes. CDB, I just liked at 111, the same as my guess. Yep. But I think you're a little late on that guess. Okay. Darin, would it be worth it to bore cam tunnel out on my factory LS block for roller cam bearings?
Factory LS? No. Well, you could only do that to an aftermarket block capable of handling that bearing core diameter. Yeah, don't do that to a stock block. Those are not meant to push that far. Could you? Maybe. I wouldn't.
Okay, one of us will check our PM.
Now, somebody might specialize in doing that. Who knows? There might be some guy out there that's found out that he could put this special bearing with this main size and up the core size and make it live. That's like when somebody comes to me with some obscure cylinder head, like a Porsche engine. I'm like, go to the Porsche guys. They've been doing that shit for 50 years. You think you're going to come to me and I'm just going to find power? No. Every engine has its own little idiosyncrasies, its problems, its issues. They know all that. They've been doing that. You know what I mean?
Jeff Ott, I've always loved cutting edge technology in racing. I remember in the 80s seeing a plastic Victor style intake from Brandywine cylinder heads on a super stock Camaro.
I think I actually remember the manifold you're talking about.
Sean Kasparian, can you talk about oil foaming? Conditions that cause it, such as RPM, vacuum, and weight?
No.
Or level? Okay.
Again, I'm not a tribologist. I'm not a petrochemist. And as far as that is concerned, that happens usually in endurance applications under high temperature and not my forte, and I don't know enough about it.
Thanks, Sean. We appreciate you being here. Ty Hewitt, that was a great video, Darin. I'll probably watch it a third time tomorrow. I listened to your presentation in the shop while I work. I might take multiple times before I really get it. Yeah, all of us do, I think. I have to watch or listen to something 3-4 times. And that's
I always thought I was a slow learner. I just found out I was just like everybody else.
Yeah.
Because when I was learning anything, like reading an engineering text or something, like I have to read it 10 times at least. And then 2 or 3 years later, I have to read it 10 times more, and then I'll get a little more out of it. And then, you know what I mean? Learning anything is not linear. It doesn't go step by step. You just like absorb all this knowledge, and then pretty soon you start making sense out of it. You know what I mean?
Mm-hmm. I do. Trust me.
In other words, that's why they call it clicking. It starts to click, you know?
Turbos welding and repair. What do you think about very wide connecting rod side clearance? How much is too much?
How much is too much depends on a lot of things. Okay, how much is too much? There isn't a pat answer for that. I mean, how much is too much for an aluminum rod or a steel rod or a titanium rod or this size crank or this size pin or this width of rod or that width of rod is different. It changes with the intended purpose and the engine combination, the architecture and the designs of the rod, crank, pin, and everything else. So there is no one amount. You should have sufficient clearance to have sufficient flow to carry the heat away and oil the thing without having too much to load the rings up. That's kind of what you're shooting for. And whatever that is in any given engine, you're just going to have to find that. And it's like anything, all the math and the physics and the everything that I tell people, you still got to get it on the dyno and beat the shit out of it for months and months and hone in on what it actually wants. There's no way anyone's going to tell you to do this, this, and this and hit the bullseye. You're going to get close, and from then, you're going to have to dick with it, F around and find out. Then the bearings, burn it up, make them thicker, give it more clearance. Oh shit, I'm getting oil past the rings. Now I need to spin it up. That's what pro stock technology is. That is what it is right there. That's what it boils down to.
It's not the years, it's the mileage. Indiana Jones. Mike G, great. Thanks, Mike. Terry Grover. Tim, you said cool cans, which I like. I think they work. But also, I wrapped all my fuel lines in tin foil back in the day. Yep, yeah. Many guys did that back in the day.
Everybody did that, yeah. I mean, back then, that's something you could see on the racetrack. You do that today, you wouldn't see anything. Unless your underhood temperatures, see, there's a case for everything. So unless your underhood temperatures are so high and your exposed lines are heating the fuel up, so you put a cool can on there and it's worth power. Well, in a case where it wasn't heated up, it wouldn't be worth anything.
Yeah, the click moment. We're all there. I think we all hit that at one time or another. Jim Steck. What's the correct sequence in dry sump system? Scavenge pump, tank, filter, cooler, pressure pump?
Correct sequence in the dry sump system. I'm not even going there. I don't know.
Okay. You know what?
Too many.
There it is. 3 hours, 1 minute, and there's no more questions. So that's perfect. See how that works out?
I did on a question I couldn't answer.
Oh, there it is. Wait. Ed Case says, hello, everyone. I got here late. We'll be watching the replay. So thanks, Ed. Take the time to watch it tomorrow or the next day, whatever you can. And that's what we're saying, guys. We appreciate you being here. I mean, we talked about that, trying to limit these live chats to an hour, hour and a half. And I'll tell you, it seems to be 3 hours is a magic moment. Now, who's going to sit there? I've heard people, I can't sit there for 3 hours and listen to it. Well, don't do it that way. Look at it like an appetizer. You take 10 minutes here, you 10 minutes there, go back and forth and see what you got. I've been trying to take, when I get time, take highlights out of some of these and make up little shorts, because people have the attention span for 1 to 3 minutes without an issue. And there's lots of things we can make into shorts. So make sure you take the time. If you're going to do that, throw it on in the garage and see what you can learn. Even if you're doing something else. Yeah.
The click.
Yeah.
That he was referring to.
Yeah. Anderson. Yeah.
That's why I have pursued this. I mean, we had the engine building school. We had the cylinder head school. We did it all over the United States, Australia, what have you. And I continued it after I left Roy Morrison, because seeing the light in someone's eyes come on when it clicks, dude, there's nothing like that. And Bill Anderson is a prime example of that. I had him in the shop for 2 days, and we practiced porting, and I showed him the concepts. He already learned the math, the concepts and stuff. And when it's kind of like port shape and everything, it doesn't click until you see somebody do it and manipulate that shape and why they're manipulating it. And when he saw that, his eyes got big. And I went, click. No. I knew right then he got it. And then he went out on his own. Ta-da.
I'm just putting down some of the guys have said, thanks, guys. We appreciate all that for sure. That you guys are grateful. That's, like you said, it makes it worth it for us to sit on our asses for 3 hours and talk to you guys and learn. Every time I'm on one of these, I learn something new. So it makes it worthwhile. That's what it's all about, is giving it back to you guys so that you can get your racing program up to snuff and better than before and faster. And that's the key. So we're going to end it here at 3 hours before. Go ahead, Darin.
There are so many people out there that have so much to offer.
Yeah.
A lot of the old NASCAR head porters, they got so much to offer. different world. They saw a lot of things. All those builders, all those people that have done anything in this industry over the last 30 or 40 years, we've all seen things maybe a little differently and had different experiences. Those experiences may never be repeated again. Do you understand what I'm saying?
I do.
The way I was brought up, that's no more. Those days are gone. I mean, how many people are going to hire a kid that's 25 years old to port their pro stock cylinder heads and give him free rein? Just so long as you make more power, go do what you want. Those opportunities don't exist anymore.
In medicine, it's always see one, do one, teach one. That's the mantra. So let's run down through there because everybody's saying bye and thank you, and we appreciate that. Thanks, Anthony. Ed's Machine, thank you for being here. We appreciate that. Brian Cool, thank you, Darin and Tim. You guys are the best. Spread the word, Brian. We appreciate that. Because I'll tell you, the things you're going to see here and learn here is something you're not going to see on any other channel, and I can almost guarantee that. And the enthusiasm, well, 3 hours and 6 minutes, that's not bad. The enthusiasm that we have from us and you, it comes back and forth in the audience. So remember, stay tuned because you never know what you're going to see, and always learning something new at DBG.
See you guys.